Actually, before I start, I've been asked to do the housekeeping things here. So I think the important one has to do with parking. So if you've parked in any of the city west car parks and will be parked for more than an hour, okay, please ensure that a valid parking permit is displayed on the dashboard. Everybody okay with that? Because otherwise you might come with a ticket. If you've parked in an undercroft car park, that's a new word. Validation tickets are available at the registration desk, and that will allow you to exit the car park at no charge. And parking permits for the rear car park are also available from the registration desk. So if you're not good to go, you think you're missing something, give Suzanne a shout up there. And I think the only other thing has to do with the restrooms. They're located in the lobby to the left of the couch. And I guarantee they're there because I found them. There you go. Okay, well, welcome. We're really pleased, excited to be in Perth. I've got Lindsay Heggie here, who's a graduate student with me, finishing up her PhD. And she and I will hopefully try to tell you something that's interesting, informative, and useful over the next 2 days. So the disc is something that has been put on. It's a yearly thing with the SCG. They select one person per year to go around and talk about an item that is they think is of particular interest and is germane. And generally, it's seismic. This last year, however, they thought they might change pace a little bit, have somebody who is talking about other aspects, near-surface aspects, resource exploration, but not using seismic, but all the other techniques, and in particular, electromagnetic techniques. So I've been targeted with putting together something like this, and yeah, we're on a mission to kind of take it around and try to provide a sense of what electromagnetics is like, where it could be useful, have you understand the fundamentals, and just to see if we can elevate the use and the usefulness of electromagnetic geophysics. So it's a little bit different than previous years. Usually the disc is a one-day affair, and we have kind of scheduled things that, okay, we could sort of do things in one day, but we've actually got a lot of material, and we're spanning basically 2 days of the disc. The first day is sort of a formal registration day that you have to go through the SCG. Second day is free. I'll talk about what we want to really to accomplish there. The other thing is that the SCG, usually the speaker of the disc has got a book that they provide. We were asked to do that, but it didn't seem like a particularly fruitful thing to do for us at this point, because by the time you compile everything in a book, especially, first of all, it's a lot of work, and secondly, by the time you kind of get it all together and you press your finger on the print button, it's probably out of date. So we wanted to have something that's a little bit more dynamic and alive, and wanted to talk about that. Our overall goal here, we've got a lot of material, but our overall goal is to try to kind of connect somehow with you to try to find out, the problems that you're doing and how the material that we would present would interact with that. In other words, at the end of the day, to be useful, right? I think in order to accomplish that, it might be very helpful for us to find out who everybody is in the room and kind of what you're doing, and maybe just a sentence about what your familiarity is with electromagnetic geophysics, why you bothered to spend the time to come here. So maybe just kind of go around the room and just quickly introduce yourself and a little bit of what you do and what you hope to get out.
I'm Cliff Ford. I'm a PhD candidate at GeoSci.xyz and studying the Carnarvon Basin with the Northwest Shelf, basically. So I'm here to find out how to interpret the EM and gravity data, mainly EM, I guess, on the Northwest Shelf.
Hello, my name is Bella. I work in UWA. I am working mainly in mesothelioma, operations, and
Shane Muley, I'm a geophysicist. I've experience working with inversions, AM inversions, but never used the UBC stuff, so they're good to see how this compares to other things before.
My name's Jared. I work at GeoSci.xyz, which is a geophysics consultancy, and just here to expand my knowledge.
My name is Mary, and I'm a postdoc at CSIRO, and my work basically was about the inversion of the multiple geophysical data sets to image across the planet. And I've never used it here, that's why I'm here. So I want to be more practical.
My name is Mike Williams. I'm from CSIRO as well. I'm leading a group of 24 postdocs and career researchers in a program we're calling Deep Earth Imaging. And Mahid is one of the postdocs. Gerhard over there is one, Elaine there is one. So I'm here to catch up on from a long time ago. I'm delighted to see Bob Parker in the notes here. I first encountered Bob when I was a PhD student in the back in the 70s. He spent a year with us today, teaching us the inverse problems. And there's a lot that's happened between then and now, so I'm just here for a refresher.
Hi, my name is Dan Lee from Fields Metals. We deal with all types of geophysical data sets, and EM is one of the primary methods that we deal with. Just to expand the applied to the exploration activities.
Regis Neroni for Fields Metals as well. Use mostly EM for mineral exploration, but finding more so lately hydrological applications, stratigraphy mapping in sedentary environments. I'm just here to brush up on my uni data sets.
Mark Reach from GeoSci.xyz. Has similar UCM primarily for urban mapping, so you can see.
My name is Roman Bilogorod. I'm currently a PhD student at the Perth University. I've never worked with electromagnetics, but probably will someday. And just here to work with my knowledge.
I'm Lily. I'm a radiologist at the I'm just here to learn how to apply.
And this game, I work for Southern GeoScience Consultants as a geophysicist. And like the others, for an EM refresher, I haven't used it lately, so.
I'm Rob Swift, and I'm a geologist from RPS. Again, I've used EM since the uni.
I'm Gerald, I'm a postdoc at CSIRO. I'm primarily a computer scientist specializing in machine learning estimation data images. And I'm thinking for applications of geophysics, I've done anything here. So that's what
I do lots of ground EM work in the field, data processes as well. All sorts of other geophysical methods as well, but I've done EM for about 12 years now, so that's what I've been recently. I'm Christian Bestia, working for a school here, and we process a lot of EM heartbeats, so it's here to increase my knowledge.
I'm Sasha, I'm a PhD student at UWA, and I'm working on the EM, ground EM, a bit of engineering with a chemical festival for principal and don't to the centre of WA, so I'm just here to more, make sure I get my PhD right. Pretty much. So, my name is Michael, and I'm a postdoctoral fellow at the CSIRO. My experience mainly process interpretation of potential field data, but some of my future projects might include EM, so I'm going to compare one steps and methods.
Jeremy Girard, I'm doing a PhD at UWA in geophysics, so I'm using inversion and I'm working on integration problems. In the past, I've been working on using inversion and running the new PhD, so I'm here for a refresher.
I'm Cam Adams. I'm a Hubble PhD student at UWA. I work predominantly in spectrophysics of ultramagnetic rocks. Apologies for being late. My name is Kat. Can I run again?
I'm Jillian. I'm an exploration geologist at IGO, and I don't really know much at all about geophysics, but I know that they use it a lot, so I want to learn.
I'm Penny. I'm a hydrogeologist from the Department of Water and Environmental Regulation, and just interested in this AM's application, showers and tree models.
I'm Sarah, and I work for a Mexico, which is a geophysical consultancy, and EM is kind of the large portion of our work, so increase knowledge and development skills.
I'm from GeoSci.xyz, Australia. My name is Peter. We do annually increase seismic survey and processing of the
And processing of data.
Yeah, yeah.
And actually, geophysicists this AI is seismic data.
Perfect. Well, you guys sound like the textbook audience. Okay, so we've got a whole range of things, right? So we've got people who have used EM for a long time, both with respect to exploration problems as well as just some other problems too. We've got large scale with magnetotelluric looking deep. We've got groundwater hydrology. I'm very pleased that people from groundwater hydrology have come. One of the big applications that we see worldwide, and especially in North America, is the use of airborne EM for groundwater hydrology. And yes, I think there's a lot of overlaps. And to make sure that the two groups can talk to each other, and so the end is not completely mysterious. So that's good. I appreciate this background because it actually kind of helps us focus where we want to go, especially in the presentation of the case histories, because we've got more case histories than we can really present. And so if we can kind of match things up with what you guys would like to have, then that would be great. Oh, I didn't turn this on. Let me try that. How's that? That's a bit better? Yeah, thanks. Yeah, I can even hear myself. So this is it, electromagnetics, both fundamentals and applications. That's going to be the theme for everything. We're not going to do a lot of the stuff in the middle, but if you understand the fundamentals, then you kind of got it, right? And then you can do the applications. And you'll see that the applications are really very informative and kind of inspiring, I hope. So first, before we start, I'd like to give thanks to Kathleen Oliver. Unfortunately, I haven't even met her, but she's been working behind the scenes, arranging all of this, and Emma Brandt, the Australian Society for Exploration Geophysics, and as well as our home group, the Geophysical Inversion Facility, are sponsoring part of this. Well, you told me a little bit about yourselves. I'll tell you a little about me. Mike mentioned Bob Parker. Bob Parker was my supervisor. In fact, I guess I was his first student, interestingly enough. And then I was at Scripps Institute of Oceanography, and there were two other people, Freeman Gilbert and George Backus, who are they're absolutely icons in the whole aspect of geophysical inverse theory. These were the people that really set the framework for how the geophysical problem could really be thought of. And their work, kind of coupled with the Russians' work with Tikhonov and Arnson, I think really formed the real foundation of where we're going. So I just want to give you a little bit of maybe background here. It kind of puts things in perspective. 1975, which perhaps predates a few of you, the kinds of problems that we could do basically were 1D problems, because you could only handle a certain number of variables, maybe 50. So that allowed you to do 1D DC resistivity, maybe magnetotellurics. 1985, we start to get the workstations that are available, handle 1,000 variables, so you can do the 2D DC resistivity and IP. By 1995, we can handle maybe 10 to the 5th variables. There's 3D, so that allows you to do the 3D problem. You kind of need extra dimension. Every time you add an extra dimension, you've got to kind of exponentiate the number of variables that you've got. But that actually allowed us to do the 3D gravity, the magnetics, the DC resistivity, and IP. So that was a huge step back in sort of that era. This continued development, one of the big things that happened here around 2005 is that the mathematicians and a number of consortia got together and showed how you could actually take a big matrix and factor it. So if you've got 10 to the 5th variables, you basically got a 10 to the 5th by 10 to the 5th matrix to work with. And solving that is pretty challenging. But if you can factor it, then you can use it to solve that system of equations many times very rapidly. And that's really what came about here. The microprocessors kind of came in here, allowed you to have multi-cores. And by this time in here, we can now solve the 3D frequency and time domain problem with at least a few sources. And then by 2015, is this thing cutting out?
Bring it down. Can you move it down? Does that help?
Does that help? I'm not sure. There. So by 2015, now with all the cloud computing and lots of processors, we can actually handle lots of sources, and both in the frequency and the time domain. And the thing that I wanted to mention here is that you put these things together, it's a combination of computing power, advances in inversion methodology, how you actually attack the problem, and you put those together. I think we're in a position now where we can solve most any problem in electromagnetics. So that's a good place to be. The other thing that is inspiring about all this is really the instrumentation and the data that exists. I mean, really, we have large numbers of data, have unprecedented quality these days, and it allows you to really tackle serious large-scale problems. Whether it's for groundwater problems of California, whether it's hydrocarbon problems for de-risking, or whether it's your OSLAP, MG problem. By the way, is there anybody in the room that's kind of connected with or very interested in the use of marine EM for hydrocarbons? Couple, okay. The next thing that has really come about and is extremely important is that we now have the web, all these open source resources that are available, and there have been extremely important. It's kind of caused a kind of a paradigm shift in the sense of it allows people to collaborate, to share, to put some stuff up on the web, to test it, to make changes, and interact as a community. That is huge because it now means that when you're working with a particular problem, you actually have a collection of people to interact with. One of the things we're going to be talking about today, well, tomorrow, I'll show you examples today, is a SimPeg package. It's simulating parameter estimation in physics. That is the kind of the underlying computational software that we're using for solving a lot of the problems that I'm going to show you today. The thing is that there's many applications. So we're seeing that kind of in this room as we went about just what electromagnetics can possibly be used for. So there's minerals. There's a few people in here involved in that. Contaminants. Stuff is always being put into our environment, getting into the water supply. There's water issues from a whole bunch of perspectives. There's geothermal energy, unexploded ordnances, hydrocarbons, slope stability, geotechnical problems. That's a vast range of problems, and electromagnetics can actually be used for each of those. So that's it. We've got the basic ingredients. We've got problems to work on, high quality data. We've got ability to invert these data, and we've got web tools to communicate. So that's great. So why is not everybody running around doing electromagnetic geophysics? What's the roadblocks? Well, there's actually quite a few. So in general, geoscientists, they just don't realize the role that electromagnetics could possibly play. So they've got a problem, but EM is just really not part of their repertoire. They don't understand the technique. The terminology is confusing. This guy's talking about in phase or real or imaginary. What are you guys talking about? And it seems complicated and it seems unintuitive, especially compared to seismic, where you've got waves going down, they bounce off, they come back up. You make some geologic sense just from the data. So those are problems. One of the biggest impediments is really trying to come to grips with what's the relationship between physical properties and my problem. So if I've got a problem, how does electrical conductivity kind of fit in, and how is it diagnostic? But even if you do kind of get through that, then there's a question about surveys, because you've got so many to choose from. You can have a DC resistivity survey. You can do something in frequency or for time. Your sources could be in the air, on the ground. And then, what do you expect for resolution? And perhaps the last one, and this is, again, something we're trying to kind of help overcome this course, is if you are, as a practitioner, are faced with a problem, it's kind of comforting to know if somebody else has had a similar problem and has used a particular technique and kind of found out how those work. So that's kind of the area of the case history. So these are the kind of roadblocks. I think they're recognized by most people. And really the goal of this disc is, let's just get rid of them. So let's just learn about the stuff that we need here so that these issues are no longer a problem. So that's it. We're in a position of basically what I consider to be kind of a perfect storm here, just because everything that's happened over the last, especially 10 years. First of all, we've got problems. They've been around for a long time. And we've got high quality data. We've got an inversion capability now that can take and invert just about every kind of data. And we've got web tools to communicate. So the disk is kind of sitting in here, and we're going to try to combine all of these things and really get rid of those roadblocks. So that's a good idea, but there's a missing ingredient. So anybody care to offer what thing has been missing there? Yes, what's been missing? Well, in a way, it's true. What's been missing from there are the essential ingredient, that is, young, brilliant, high-quality people that really kind of fill that. We got one of them sitting over there. There's another person who comes with me, so the first few legs, soggy. But this is representative of a community of young people who are really, connected with open source computing, are driven by using new technology and being determined to really kind of solve new problems that are important. So that means that with all that, we're kind of good to go. So the goals for this, I want you to see a variety of potential applications and to illustrate the effectiveness of EM in helping solve those things through this case history. So that, I think, is just, for me, that's just kind of inspiring. You just see what the problems are and how the EM has been applied. In doing everything, building a foundation is really important. We need to understand the basic principles of EM, and because without understanding the basic principles, you don't really know what your foundation is, what your building is really structured on. And we're going to try to do this in a bit of a different way. There's not going to be a lot of equations in this course, but we've been developing interactive apps that people can play with that allow you to ask questions and get some information out. And pictures are really very valuable. And we've got an open source resource, GeoSci, in which we're continuing to put on basically all of our material. It's open source. So that's the material that you use in the place of a book. Also want to set realistic expectations. Electromagnetics over the years, as probably everybody knows, has sometimes been oversold. People come along with a new idea, and everybody kind of jumps on because, in principle, philosophically, it looks like, oh, that's great. But then there's often practical implications like, well, it doesn't really work as well as I thought. It doesn't have a resolution. So we want to set those expectations so that you got an understanding of what you might be able to get out from the geophysical survey. And then last, and this is actually very important, because we want to build a community help, or at least help the development of that. So that can be done by developing and promoting open source software and capturing case histories worldwide. So that's the goals for the disc, and yeah, I'm hoping we can accomplish that. I want to talk just a little bit about the resources. So here's our source GeoSci. For those people who have a background like me, how many people actually recognize that image, that book? That's pretty good. It's about a third of the people. So this was a book published by the SEG, edited by Misak Nabigyan, who's really a guru in time domain EM. And it's got both the theoretical background as well as case histories. There's a particular chapter in there with Warren Coleman. I think that everybody who comes through a university and is doing electromagnetics probably has. So we've got GeoSci. The idea is to turn this book into something that's a little bit more alive. It's got some interactivity that's associated with it. And so it's got information as well as the case histories. Case histories, I think, are very important because they provide a way for us to talk about that we're working with. And what we've done is to parse our case histories out into what we call a 7-step framework. And everything that we do is going to be kind of put back into that framework. And I think for any practicing geophysicist, you'd say, well, that's really reasonable. Because the first step is the setup. Okay, what's the problem? Second step, what's the physical property that are relevant and what's the information about them? Third, okay, what survey are we going to use? DC resistivity, airborne, whatever. Fourth, what data do I collect? How do I process the data? What's the processing that's going on? So it just could be, filtering. It could be inversion. Go from that. Then, what am I going to use? I've got the output of my EM. What's my interpretation, my geologic interpretation from that? And then the last part is the synthesis. Like, okay, how does all of that stuff impact upon the initial problem? So I think this is a logical way. I think pretty well everybody who does problems kind of thinks in that way. We just formalize a little bit so that you can tell which step you're in. And that greatly enhances the communication. If you're working on a particular problem and you codify it into a 7-step process, and you've got down to basically something like the data or a problem here, it's really easy to communicate with people. Like, okay, in 3 minutes you can tell exactly what my problem is, where I am, and I'm stopped. So it helps promote that communication. And the fact that all of this is live on open source media means that you can actually comment on stuff that's here. You could add stuff. Like and everybody knows something that, or views something in a particular way that other people don't. And it's an opportunity to contribute to the community and to gradually build this up. We're going to use what we call apps, and we've been developing them for a number of years, and we'll have quite a few of them to show you today. But they're great, and the reason that they're great is the following. I mean, if you look at Warden-Holman, and here's Maxwell's equations, it's like, okay, I understand all the pieces, I understand all the little symbols that are there. But it doesn't give you any intuition about what's going on. There's no image that's available. So the apps that we have are generated in something called Jupyter Notebooks. And they just got slide bar parameters and allow you to plot things. But the important thing is it allows you to ask questions. And we're going to use the apps throughout the day, and we're using them a lot more tomorrow. So when you take a problem, the very first thing you're going to do is to try to anticipate what the outcome is going to be, and then you actually use the app to find, like, okay, was I right, was I wrong? And those are the ways in which you kind of learn. You do something, you look at the output, and you really try to make sure that you understand. So it's a much more engaging way of learning, and it's much more effective. So how are we going to achieve our goals? Well, we're going to connect to relevant applications, essentially help to go around here. Select a particular type of survey. Use the apps to explore, ask the questions, and we'll show the success through case history. So that's going to be kind of how we'll parse our way through things. Now, the agenda for the day is big. Okay. We toyed with this, but really, if you're using electromagnetics, there are so many different applications in so many areas with so many instruments that what we're decided to do is to take the challenge on presenting to you in one day kind of a holistic view of electromagnetics. That's a big thing, because if you go to university, you might take a class on DC resistivity, or you might take a class on this or that or that. What we want to do is to kind of get rid of virtually all the stuff, and we're going to go through it the following way. We're going to start off with DC resistivity, which is kind of forms the foundation for many parts of electromagnetics. Then we're going to do the fundamentals of EM. We'll do inductive sources. So these are sources that do not have a direct contact to the Earth. That might take us to lunch. Then after lunch, we're going to do grounded sources. So here's where all of the marine EM types of things come in, but there's also, you do things on ground. Natural sources, that's the magnetotellurics problem, or Z10, if anybody uses that. Ground penetrating radar is just electromagnetics at high frequency. And then, I'm not sure how many people here are interested in that, but certainly induced polarization is extremely important for mineral exploration and potentially for water issues and a lot of other things, and then the future. So that's the goal. We're actually going to kind of step through this in little packages, and we're going to build on things. So I think what's going to happen is how many people here are familiar with DC resistivity? And who have done a DC resistivity survey? Or raise your hand if you know what pseudosection is. Good. Okay. So yeah, you're going to do some stuff in here. I'm going to talk about DC resistivity, but we're going to present it in a slightly different way, or with a little bit of a different bent, so that we're really connected more with charges rather than currents. And we're going to use this to gradually build up. So we're going to start here, learn something about here, use that in here, and then we just continually to build up so that by the end of the day, we can actually tackle some problems that have a lot of stuff in them, but you've got the background pieces and like, okay, I got it. That's not too bad. A touch of realism. It's a big agenda. It's yeah. You'll see a lot of stuff, and there's a variety of people here, different backgrounds, different expectations. There's some people here probably have a pretty serious background in electromagnetics, and maybe you actually know most of what I'm kind of planning to say. We're not really targeting for those experts, but if you are an expert, then here's a quote. I go for coffee with my wife every Saturday morning. We have a group of people. We've met at the same coffee shop, the same time for 23 years. And every day that we go in, there's a new saying on board. And this one I really like. It's by a gal named Doris Lessing. And she says, that's what learning is. You suddenly understand something that you've understood all your life, but in a new way. And that actually, I think, also turns out to be important. It just enriches your spectrum for how you think about the problem. So maybe for those people who are experts, it's a learning that. The DISC, I mentioned before, it's a 2-day event. So the day 1 is the DISC course. This is officially sponsored by the SEG. That's what you pay a registration fee for. DISC Lab tomorrow is sponsored by GIF. Doesn't cost you anything. Our goal there is as follows. First of all, we may not cover all the material that we would like to do today, because I want to go at a relaxed pace. There's no sense in just doing a complete core dump of stuff, right? And so let's go through, talk about things, make sure we kind of understand things, and if we don't quite get through it, there's tomorrow. We could pick it up tomorrow and do an hour or two to kind of finish up. The thing that we would really like to do is to get you to talk to us about the problems that you are working on. We've done this around the world, and it's been really insightful. The idea is that I will ask how many people would volunteer to give a very short talk, 5 minutes, can't afford to do anything more. A very short talk tomorrow. You could either do it with a couple of slides, or even if you just sort of stand up and talk. But just communicate. Oh, okay, guys, here's my problem, and here's my connection with EM, and here's what I'm doing. Here's what I'd like to accomplish, and here's where I'm stuck, or here's my success. As we go around the world, and we do that at each place, we capture them, put that some kind of summary up on YouTube, and it becomes a very valuable resource where people look worldwide. And you say, oh, well, in India, they're doing these kinds of problems. And in Australia, in Perth, these were the kinds of things that people were most interested in. And I think, again, that's another piece of information that can just help the development and growth of a community, because you just start to get connected with other people that are perhaps working on that same problem. So we'll try to capture your local applications. We'll store them on the web. And yeah, we'll ask you at the end of the day who would be willing to participate. I do strongly urge all of you, if you possibly can, to come tomorrow. The SEG is pretty big about like, okay, this is a 1-day event, right? But it's not a 1-day event, it's a 2-day event. There's a lot of overlaps, and at least make sure that you can come for that first half. Yeah, so eventually we're going to do, hopefully maybe 30 odd locations to capture all those applications that people are doing, build a community, will be in much better shape. And then also to connect and contribute, there's something called Slack. how many people have heard of Slack? Okay, so for those who haven't, it's a way that you can communicate with us. It's a channel. We'll make open up a conduit here so that you can ask questions, or you could post a picture, or you could make a comment, or whatever else. And that's a way that you can interact as we're doing things now, but it's also an important way of interacting. And yeah, then we're inviting people to contribute to EMGs, either case histories or content, and also our software environments. So that's kind of where our goals are. And I think now just sort of start just kind of a basic introduction to you. First of all, anybody have any comments or questions? Pretty general stuff, but I think it's important to kind of have an overview of like, okay, what are we actually going to do for the next couple of days? How is it going to be structured? Okay, so let's look at electromagnetics. So there's 3 problems that we'll kind of use as just sort of representative. We're not necessarily going to work with all these in detail, but you know, we've got mineral problems. So how do we locate and characterize mineralization? Unexploded ordnances. Is there anybody in this room that's connected with UXO? I think it's more the Brisbane group. And water issues, and I'm glad that there were some people here in groundwater hydrology and concerned with water. So the properties. So there's electrical resistivity, electrical conductivity. So we're going to use them both kind of intermittently, but resistivity is connected with how easy it is to pass current through a particular law. And low resistivities means it's really easy to pass through. High resistivities means it's not. So it varies by many orders of magnitude. On this scale, it's about 7 orders of magnitude. Massive sulfides have a resistivity that's very low, way less than an ohm meter. That's the unit. And you go to igneous and metamorphic rocks that have very high resistivities. A lot of the materials that we have, tills, clays, hydrocarbons, kind of lie in that meter background. But there's a couple of things to take away here. One is that resistivity varies by orders of magnitude. Secondly, any particular rock that you have, even if it's a high resistivity, could have variation of a couple of orders of magnitude. There are certain things that are have very low resistivity: massive sulfides, graphites, salt water. And also the other thing that's important is that if you know what the resistivity of something was, okay, that would not give you enough information to tell you exactly what the rock is or what the object is, right? Because any particular resistivity up here could be a metamorphic rock, a till, okay, so there's no unique relationship here, but there's a table of values. Dielectric constant, given this audience, how many people have been connected with GPR studies or interested in GPR? A couple. We'll see. This might be something that's worthwhile for Disk Lab or something like that. But anyway, the other property for electromagnetics is dielectric. Well, it's called electrical permittivity, but it's cast in terms of something called dielectric constant. And it has variations too, mostly depends upon the water content. Magnetic susceptibility is also part of electromagnetics. Again, it has a wide variety of variation, varying from orders of magnitude, with things like magnetite being the most magnetic, and sediments and igneous rocks being sediments especially having very low magnetic susceptibility. So magnetic susceptibility is the ease with which a rock acquires a magnetization when there's an input. to kind of use this diagram for a bit. It's sort of an icon that kind of keeps us together. The main parts about a geophysical survey is that, okay, we've got a source, we're going to input some energy, we got some physical properties. Actually, I didn't explicitly mention conductivity, but that's the reciprocal of the resistivity. So very resistant rock is very conductive. And so we've got these physical properties here. That's going to generate some data, which we can measure. So that's our kind of icon to kind of keep us on track. So here's our basic equations. I said I wasn't going to go through a lot, but we actually have to write out Maxwell's equations. These are Maxwell's equations in time. These are Maxwell's equations in frequency. And there's a few laws in here. B is the magnetic flux. E is the electric field. And tell you how a change in, let's say, a magnetic field affects an electric field, or how a current density J affects a magnetic field. So these are the physical equations, Maxwell's equations, and we've also got what are called constitutive relationships that relate the fields and the fluxes. So here we've got an electric field, electrical conductivity, and a current density. So that's a field, that's a flux, that relates them. So for B and for H, and there's the magnetic permeability in B. So these are the things that they're carried out in the laboratory that tells us what the relations are. So the basic equations can be done in time. We'll work through them. And they can also be done in the frequency domain. And we'll generally keep track of these by capital letters and small letters as to which domain we're working in. So those are the basic equations, and that actually forms the heart of everything that we're going to do today. We're going to solve those equations with different sources and different boundary conditions and see what the result fields are like, and then also convert those. So let's now kind of take a look at electromagnetics, and let's think about, first of all, sources. So we need to put energy into the ground, and we have a choice of sources. There's going to be an inductive source. So here's a helicopter. It's carrying a loop. So there's a generator that's attached to that. There's going to be a current that flows in that. So that's going to be your source, and you can fly this guy. So you notice there's no contact with the ground. So it's called inductive. It could also be a grounded source, or put two electrodes in the ground, have a generator. So those are the types of sources that we'll talk about. Then there's a waveform. The waveform, that's the current in the transmitter, could either be harmonic, just like a single frequency, or it could be more of a transient time domain experiment. So it could have an on time and then off time and reversible. So those would be the waveforms. And then there's a location of that source. It could be airborne, as it is within this system. It could be on the ground, or you could actually put something in a portal. Okay, so that energy goes into the Earth, interacts with material properties that are there, and gives rise to some fields that you can measure up here. So those are the data. And then your choices are like, okay, which field do I want to measure? Do I measure E field or B field at the frequency, or the same in time? You could also measure EV or the time rate of change of V. And then which frequencies? Be low frequency, high frequency, or if I'm in time domain, which times? And then in addition to complications, so now you've got a field. So a field is something that's in 3 directions. Which component do I want to measure, and where are those components? Right? I could measure something in the air. So on the airborne system, there's often a receiver here. On the ground, for the magnetic tellurics, for instance, you could put out some E field receivers and some B field receivers. You could also put stuff in. So I think the thing about this, you're starting to see like, wait a minute, there's a lot of possible choices here in setting up this experiment. So let's go back to our three problems. And really the thing I really wanted to mention here is that we know we have three problems, but electrical connectivity is diagnostic for all of them. So virtually all of today, we're going to be talking primarily about electrical connectivity until we get to anything that connects with GeoSci. So that's kind of the sort of the introduction. What I'd like now to do is to look at the first of the major components. That's DC. So while I'm changing, anybody got a question? There we go. So DC resistivity, one of the oldest geophysical techniques, is still incredibly useful today, and it forms a foundation for a lot of the things that we've done. And it's, I don't know how you guys learned about DC resistivity, but there's a number of ways that you can kind of think about formulating the problem. Some people like to think in terms of currents, some people like to think in terms of charges, or some in both. I'm going to give you a presentation that really talks very integrally about both currents and charges, but there's an insight that comes with respect to the charges that's very important. So it's the currents that kind of tell you something about how everything is connected in the ground. But the ultimately the data are connected to some charges. And I think it's really interesting just to kind of get that concept, and because it just adds a lot of insight later as to how things could possibly be understood. So that's kind of where we're going to go. Here's our DC resistivity experiment. We've got a source. We're going to look for the resistivity. I'm going to measure some data. So what's our motivation here? Mineral exploration. I'm going to show you a case history that's actually connected with an Australian deposit. Water flowing in mines. If you're in a mining environment, water is definitely your enemy. Oil and gas, there's all kinds of applications for DC resistivity. Groundwater, DC resistivity has been used in many, many cases, and also in geotechnical problems. So there's a few motivating examples. Electrical conductivity, as I said, or resistivity, so I'm flipping back and forth between them. Here's the slide that we had before. I think the thing to remember is for for resistivity, it's actually kind of complicated as to, if you have a little rock or a chunk of rock, like, okay, what's the resistivity of that rock going to be? Simple. Here's a small example. It's not a very big example. There's a penny. And first of all, your resistivity is going to depend on the type of rock, but it's also going to depend upon the porosity of what that material is, and the nature of whatever fluid is in there. So whether it's a salty fluid, a brine, or whether it's fresh water, and then how all those little pores are connected, and then the metallic matrix, or the matrix of the solid component. So that's a lot of variables, and you can appreciate that any particular rock might have a different kind of combination of these things and give a different resistivity. So what I want to do is to going to outline the basic experiment. We're going to talk about currents, charges, potentials, a bit about soundings and arrays, data pseudosections. Sensitivity is an important issue. One's always wanting to know, okay, can something work? Can I detect it? A bit about survey design, and then a case history of Mount Isa. So the basic experiment. We've got an ore body here. In fact, this is from the Allura deposit. It's kind of a cartoon that's associated with that. So this region up here is very resistive. It's a Gaussian. There's a very conductive core here that's heavily mineralized, and this outside region here is kind of just background host rocks. So these are a couple hundred ohm meters. The Gaussian might be closer to 1,000 ohm meters, and this is more like an ohm meter, right? Good. So that's what I want to find, and I want to use an electrical method to do that. So what am I going to do? Well, I'm going to set up an experiment where I first of all take 2 electrodes, plunk them into the ground. And so this is going to be my transmitter. So I've got a generator that's connected to this with the blue, and I'm going to put current into there, and that current is going to flow and be distorted because of the existence of this body. And I'm ultimately going to measure some response by having a voltmeter up here, so connected to 2 other probes, and just measure the voltage. So I've got a current that's going through, and that current is going to preferentially flow through a conductor. So you can see how it kind of is kind of being sucked in here, and it flows kind of around a resistor. What we're going to talk about is that, okay, so that's how the currents flow, but why do the currents change? Why are they changing direction in here? And then is there any manifestation of what happens? And it turns out that there's charges that are being built up on the outsides of this object. And those charges then give rise, by Coulomb's law, electric potentials, to the electric potential that you measure. So that's the basic experiment. We're going to walk through that a little bit more carefully. We've got apps that will show you later on to kind of characterize this. But you got the transmitter, currents go through, they get distorted by whatever object's there. That distortion is characterized by charges that are being built up, and now Coulomb's law tells you what that response is at the surface. So that's fine, but if we just measure the potential light, how do we get the resistivity? So we want to somehow be able to convert from those potential measurements to resistivity. So let's carry through that. So let's go back to the equations. So here's the equations that we had before. So those were Maxwell's equations. But now if we're just going to put a current, and it's going to stay constant. So there's nothing that is going to change in time. So all the time derivatives go to 0. That means that we have steady state Maxwell's equations. One looks like this. Tells us that electric field could just be the gradient of the scalar potential. And we've got Ampere's law, which reduces to this. And we've got that constituent relationship. This one's called Ohm's law. And we put all these guys together, and we end up with an equation that looks like this. So this is div, that's the divergence operator. Sigma, our conductivity, grad, V is a potential, is equal to I, a current, times a delta function, which just simply says, okay, that's the location of this point. Now, the interesting about that is if you have a very simple case, we just have a homogeneous Earth, or half space, and you put a single current in, then you actually can predict, there's a solution that tells you that the voltage that you measure looks like this, or it's got this kind of a relationship. that depends upon the resistivity, the current, and the distance that the voltage measurement is taken from the transmitter. So let's just kind of take a look at this. So suppose I've got a uniform half space, and I just plunk a current in. Then how do you expect the currents to go? You know, everything's uniform, so there's nothing that's preferential. So the currents are just going to kind of flow out in all directions, and that's what the currents would look like. And if I looked at the potentials, if I sort of right at the current electrode, the potential is infinite. And as I go away, it falls off as 1 upon r. So if I'm sitting here, I've got a potential that looks like this. Now, I could take this analytic formula and I could just rearrange it, and I could write rho is equal to this one. I know what the current is. I know what my distance is, and if I measure this potential, then I can get a value of the resistivity, which in this case was 500 ohm meters. So if you think about that, that's kind of interesting, isn't it? Right? You take a homogeneous half space, 500 ohm meters, and you just simply plug a current electrode in, and you just measure a voltage someplace. Doesn't matter where it is. Just get that number, put it in the formula, and you get out the value of the resistivity of the half space. So that's the connection. That's the basic connection of how things go. The reality, however, is that you can't actually perform that experiment. You need to have 2 electrodes for a generator. So you've got a generator, it's got an A electrode and a B electrode, which is positive and a negative. And if I have a positive and a negative current source, now you can see what the currents would do. So now inside the Earth, the currents are now going like this, right? So here they're leaving the A electrode, they're coming into B, and so here's now the current. So it's a very different current path, but that's what they are. That is going to set up potentials. And if I measure, so this green line is actually the potentials that I would measure. And I can pick 2 points. I don't care which 2 points they are. I can take any 2 points in here and measure that potential difference. Okay, so that's what a voltmeter does. Measures the potential difference between one end and the other. This system here is just a linear combination of what we had with the single system. So I could combine them. So I could write my potential difference in this matter here. And this stuff here is that's just geometry. That's the distance between the A and the M electrode, A and the M, da, da, da. So we know all that stuff. And we're just going to call that G. Sometimes it's called a geometric factor. And then we have, rearranging this, we've got the resistivity is equal to delta V that you're measuring divided by I times G. And if I could I took these 2 points, plug them into here for delta V, calculate it out, and I've got 500 meters. Okay, so that's now getting pretty close to what we would do with having a field system where we got positive and negative currents. Okay, so if you didn't see this one, okay, so suppose we change things now, right? So in this case, we've got it's just homogeneous Earth. Good. Okay, now let's change it. So suppose we put on an upper region that's got a low resistivity. Okay? What do you think is going to happen then to the currents? Mark, since you people know at this point.
There'll be a higher current density.
Right. So the claim is if we put a region up here of low resistivity, then preferentially things are going to get. It's just an easier path for the current to travel, and you can see that there's a flow in that top layer and less. Okay. So that's how the currents go. And then what about the resistivity that I'm going to measure? Well, I mean, there is no real resistivity. You've got an Earth that's got, you know, a layer on top and something below, so you don't really know. But you put that measurement, whatever delta V that you got, plug it into your formula, and you get out something that has the units of resistivity, but it's not the resistivity. In fact, you don't even know what the resistivity is, but we call it apparent resistivity. So this is sort of like the resistivity of a homogeneous Earth that gives rise to that same number. So that's the apparent resistivity, and in this case here, that apparent resistivity is 226 ohm meters. So that's kind of interesting. Actually, I didn't tell you. Was it up here? This upper region here has resistivity of 100 ohm meters. The bottom is 500. And you can see the currents. There's a lot of currents that are kind of up here, but there's some currents that are going in there. The end result is that the voltage that you measure is a little bit sensitive to everything, and having an apparent resistivity that's between 100 and 500. Okay, that's not. Later on, perhaps just after coffee, I'll kind of take you through an app that shows a few of these things. But we have apps that allow you to experiment with this. So you can put in layers of different thicknesses and change the resistivities, change where you have your A and B electrodes, your M and N, your different resistivities, and then you can plot out potentials and currents and things like that. It really helps kind of give you some insight into what's going on. Something that is perhaps familiar to a lot of people, but not necessary to everybody, is just the concept of soundings and soundings and profilings, soundings and arrays. And perhaps the simplest idea is a sounding. And in the sounding, we take an array that we have. One common one is a Wenner array, where everything is kind of equally spaced. Or there's Schlumberger arrays that have slightly different geometry. And we take that system and we progressively expand it. And what we're going to plot on this axis here is something to do with how big the array is, so like AB upon 2, that distance between them, and then what that apparent resistivity is, and then we're going to get a curve out that looks like this. And the idea is that as we look, when everything is small, at a compact array, you're kind of looking close, and as you get farther down, you're looking down. So that's going to be the kind of concept that we look at. So we'll show that here. If I take that Wenner array and just have a very short distance between them, so you can see what's happening. So this is still a layered space. Currents, here's the A, here's the B, and the currents just are kind of more or less confined to that top region, and the voltages fall off really quickly. And if I generated the apparent resistivity at that point, I get almost 100 ohm meters. So it's really close. I'm just basically sampling that top layer. If I move them farther apart, so now you can see a bit more current that's coming in here, the apparent resistivity increases a bit. So it's now 125. If I make it 30, now you can see the distribution of currents, and our apparent resistivity is now getting up over 200. So the idea with a sounding is that you're basically staying in one place, especially if the Earth is 1D. You just kind of gradually increase the size of your array, and you're sort of looking progressively deeper. An important thing here, we'll come back to this later, it's going to make a point, is that we still haven't reached 500 ohm meters here, so we haven't really got a thing that's so long that you don't see that top layer. In order to do that, the scale of your survey actually has to be many times the thickness of the layer that you're trying to see through. So that'll play a role a little bit later. Okay, so we've got this apparent resistivity curve. That's not the Earth's, what the Earth's resistivity looks like. We actually want to do better than that, to try to find out what the resistivity structure is. So we're going to invert the data. So the process of inversion, and I'm going to show you a lot of inversion results, but we're not going to go through the details of that. That takes us off a little bit farther than we want. Tomorrow, we can provide some simple tutorials which look a little bit more into the nuts and bolts of inversion, but we're not going to do that today. So here's our data, and now we somehow want to go back from the data back to a resistivity model that would reproduce those data, and it's got reasonable geologic structure on it. So that's our goal. We want to go from data space back to a model. So let's now, that was a little bit for a layer space, but let's kind of look at what happens for a confined body, because now we can get back to these charges. So if we've got a steady state solution that's going on with our currents, then that means that across this boundary, the normal component of the current density is continuous from this side to this side. But remember, we had Ohm's law, J is equal to sigma E. So that means that the conductivity, this is unit 1, sigma 1 times E1n, that's the electric field on this side, is actually equal to sigma 2 E2 on that side. If sigma 1 is not equal to sigma 2, then the electric fields are different. And if you remember from first year of physics, right, the only way that you make an electric field discontinuous is if you have like a sheet of charges, right? Because if you have a sheet of charges, got positive charges there, then the electric field goes up this way, goes up that way. So the electric field in a particular direction is discontinuous. So that means that for the fundamental thing for the DC resistivity experiment is that there must be charges that are built up on any boundary across which there is a conductivity contrast. And now once we've got those charges, then the relationship between those and the electric field are just given by Coulomb's law. So that's sort of the real basic kind of physics of where these charges come out. So let's now look at some of these examples where we've got, let's say we've got a buried sphere in here. So we've got a current that comes in this position here, and the current flows into this region, is distorted by this conductor, so they're kind of sucked into here, and then they eventually flow back. So those are our total currents. If we look just at the secondary currents, so that's being the difference between the total currents and just the primary currents that we've shown earlier, then those secondary currents now look like this. The charges that are built up are now something like this. So as the current kind of flows into here, there has to be a discontinuity in the field because we're going from a resistor to a conductor. So there's a negative charge that's built up on this side, and there's a positive charge that's built up on that side. So that's sort of what would have happened if we just had a sphere, and then here's the potential that is generated from those charges. And you can see how at the surface there are certainly things that are changed, going from blue to green here, but that's actually going to be our So now we could go ahead and say, okay, well, what would happen if we actually went ahead and measured this stuff? So let's look at a system where we're going to keep the currents in a fixed position, and now we're going to take our electrodes here, and we're just going to kind of, these are potential electrodes, we're just going to move them across like that, right? And then what are we going to measure? At each point that we measure, we've got a voltage difference. We can compute that to an apparent resistivity and see what that looks like. So here's our resistivity model. This 1 ohm meter conductor gives us this. Our apparent resistivity, if we measured them right in here, would actually been 430 ohm meters, which is less than the background, right? The background's 500. So it's seeing something. It's not 1 ohm meter, which the body is, but it's seeing a dip in that resistivity. And depending upon where we put it, if we measure over here, we actually see something that's not 500, it's a little bit more than 500. You might ponder a little bit at this point as to how a measurement could actually exceed the background if we have a conductor in there. You can think about that. We'll come back when we do the when we look at the app. It's kind of interesting. You've got a conductor, and so you think like, oh well, everything. You know, if I measure anything, it should have a little bit of it should have a response resistivity that's less than the background. There's nothing that's more that's higher in resistivity. So you can think about that. So depending upon where you are, you've got different apparent resistivities. So that leads us to the concept of profiling. So in profiling, we pick a geometry. So let's suppose you've got A, D, and N, and we're just going to move it across. So we're going to do that over across here. And for a very short offsets here, just like 4 meters, we go along and basically we measure 500 ohm meters. So we're not seeing this quantity down here. On the other hand, if we make our array bigger, and that's actually going to mean that currents are going to go down in here, then we're going to end up with a profile as we go across here, an apparent resistivity that's high at these ends, and then drops down to maybe much less than 500, and it comes up like that. So there's a couple of interesting things here that are important. One is that if for each survey that you have, you're going to have kind of like a depth of penetration or a sensitivity that's attached to it. And if things are really small, all close together, you may just be seeing stuff that's happening in your surface. As you make things larger, then you might see deeper. Okay, so that's important. We'll cross this many times throughout the day where that's actually useful. So that's the thing. Somebody talks about sounding, somebody talks about profiling. Sounding, you got an array, you expand it, you go deeper. Profiling, you're just coming along and you're trying to see if there's some response. So Mark in this case is really resistive, and I'm coming along and I've got a big resistor in my apparent resistivity profile, and it decreases. And then if I want to see something at the back end, then you need to make things even larger. Basic surveys. Here's a whole bunch. You'll hear all these names. Wenner and Schlumberger are two that just kind of talked about. There's something called gradient array. I'll show you an example of that. So in this, we could just take an A and a B electrode and just put them out there and they'll just keep fixed. And then take potential measurements and just run them along inside a region in here. So there's really only one set of currents, but we're measuring potentials at a whole bunch of different places. And then there's these things here called pole type. In reality, we always have to have a 4 electrode system for DC resistivity, but sometimes you could run one electrode out into a long ways away. So basically it's at infinity. And you could do that with a potential electrode and a current electrode, so that the only 2 operational electrodes are this one current potential. So then we call that a pole. Or if you had this, you could have a pole, dipole, or you could have a dipole, dipole. So now we've got. So those are terms. You'll see them, and just important to kind of recognize where they're coming from. We need to plot data, and traditionally, and this is still very much a way of trying to image the, to at least portray the data. So for DC resistivity, the oldest way of doing it, which still works today, is basically something called a pseudo-section. And the idea here is that if I'm measuring, here's a current, here's potential, and I just want to plot them on some kind of a plane, right? I want to have actually look at my data. I'm just going to draw a 45-degree angle down this way, and then at the intersection here, I'm going to plot the number, whatever my pair is. And then if I move this guy, he's going to plot down deeper. And if I move again, plots down deeper, right? So for the location of this current, as I move the potential electrode out, it just plots deeper. So what's happening here is that we're just kind of making a survey, doing what I just talked to you about, right? So keep moving the current transmitter along and then measure the potentials. You get values, plot them up, contour them, and now you got a picture. Well, so there's a picture of your data. And the reds here are low resistivities, the blue are high. So that's a way of plotting the data. It's great for quality control because sometimes you'll see, a value out here. This value here might be blue or something, just something that's completely discordant. It helps you, decide what's there, or as far as quality of data. This image is, is sometimes thought to be geologically interpretable. Generally, it's not. Show you an example. Here's what it is. So here's a pseudo section, DC resistivity survey. It's a single block. So that's a conductive block, 10 ohm meters, and a half space of 100 ohm meters. So you do the DC survey over here, and actually you get something that's kind of simple and semi-reasonable. So in this particular case, a trained eye or somebody with experience might say, oh, actually, I think there is something here. Let's go ahead and drill that. And in that case, you did it right. That doesn't happen very often. You take little bits of pieces of conductive material. You got little clays, piece of graphite up here, and then you do the pseudo section. Actually, it looks like this. So it's completely mucked up by all of this stuff. So the point of this, you can't go from this to a geologic image. There's no way you're going to see this guy. Here's another example, long-term from us. So there's variable conductive in the upper layer in the overburden, and there's two blocks, or two conductors in here, and there's a valley, and the resistivity pseudo section actually looks like this. So if you're looking for the low conductivity anomaly and you decided to drill right through this guy, that would mean drilling right through here. So you'd have missed everything. You'd have gone in between the two of them. So clearly looking at the data or making interpretations of the data is a really risky process. So that means we got to invert the data. So again, we're going to have our survey, take some measurements, and invert them to recover whatever our model is. So that's our process, and we can do that. Been able to do that for a long time. I just want to show you what it looks like on this example here. So here we got a buried prism. So it's a conductor. Here's our data. this one I just showed you. If we actually invert the data, then we get something that looks like this. So it's centered about the right location, and it's smooth. It doesn't have sharp boundaries, but that's because of the nature of the inversion algorithm and things like that. Again, that's something that we can talk a bit about tomorrow. And then the bottom line is that this is now a pretty reasonable geologic representation of what was there. If we come back to this guy that had all the muck in it, we end up with this. So not only do we see the thing that we're looking for, we actually have characterized the little pieces up top. So in the thought process here is, well, that's just junk. It's just geologic noise. But it actually might be that some of those are interesting. So the fact that we can, get information about them, I think is a really good thing. And then if we come back to this model here, there's our data, you invert them, you get something. So that's great. So go from the data to the pseudosection. Pseudosection is a great way of plotting the data, and we can invert them. And we can do this in 2 dimensions or 3. And that brings us to the next problem that, okay, the world is 3D. So lots of things can happen, right? So we've got the target, can change in size, change in depth, shape, right? So lots of variables. Everything can have a variable resistivity. The background could be. Got lots of things like topography and that. So that starts to lead to some really kind of serious questions, like, okay, let's suppose I've got an ore body there. Like, what do I do? Where do I put my currents? Should my acquisition be 2D or should it be 3D? Where should I make measurements? And which measurements do I want to take? And what's the effect of topography? So these are all serious questions that anybody who's doing a practical field survey is up against. And now you're at like, okay, how do I tackle that? There's no black brush that has a complete recipe on what to do, but there's certain fundamental things that you can think about that help you a lot. And the crucial element here is something called sensitivity. So if I were to ask what people's, for anybody who's done any sort of the mathematical aspects, sort of a mathematical explanation or definition of sensitivity, anybody volunteer what they would think what that word means? Is it your name?
Jared.
Jared, yeah.
It's basically, I guess, how much something subsurface might influence the survey.
That's pretty good. Anybody else? Yeah.
From a mathematical point of view, how much a change in a model would affect the predictive calculated measure data?
Perfect. Yeah. So that's kind of what Jared said. I'm sure your name is?
Regis.
Regis?
Yes, perfect.
Yeah, so here's here's our system. So we got this thing down here that we're looking for, and we set up our system. Here's an A electrode, B electrode, and yeah, we kind of want to know, are we sensitive to this target, right? So we're going to quantify that by like how much the data changes if we change a parameter in the model. So maybe I'm going to change the size, maybe I'm going to move things out, whatever the parameter is, and that gives us a number that we have as it gives us a number that kind of tells us how connected we are. So if G, our sensitivity is very big, it means that a change in this physical property, or the parameter P, has created a very large change in the data, and that's good. So I want to have good sensitivity. So in order to collect data that are sensitive to the target, there's actually two things, and I think it's very fruitful to sort of divide these things out. And the very first thing is, that's it. Let's not think about anything else. That's the first thing. And then the second thing is that we need to have a sensor that's somehow close to the target and be connected with it. So we're going to break it down into those two parts. So let's just do that throughout this whole day. We're always, when we're talking about physical experiment, very first thing is that we're going to talk about exciting the target. We're not going to jump to the data. That'll be a second step. So here's our example that we talked about before. We've got our currents. Here's our conducting sphere. You see how things come in. So here's our secondary currents that look like this. So it's clear where this particular geometry is exciting the body. We've made a difference here with and without that body. And there's extra charges, and here's our potential. So we're good to go on that. So what about the measurements? Well, we've got all of these charges that are being built up, right? And we know what kind of an instrument that we have. We're just basically going to measure the electric potential difference. So that means that we want to somehow be measuring so that we're as close as possible to these charges, and that we understand what the relationship is between these positive charges and the electrons. So our secondary potential is going to look like this, and we want to make sure that we've got a big enough span here for measuring that potential so that we have a big enough number. A thing that's going to be very important here is coupling. So if we take our currents that look like this, so let's suppose we've got A and B, and now we'll put in a plate. So if we put the plate in this way, then our currents kind of come through and they get kind of sucked in through there. So there is some sensitivity. If we put the plate this way, you can see how the current paths change. So the take-home message here is that the sensitivity is going to depend a lot on the sort of that coupling and the orientation of the target that we have with those primary currents. To actually play a role here is just the conductivity of the target itself. If we have a conductive target, so now the currents are kind of going to get sucked in through here, and so there's changes that are happening, and those are the charges that are being built up on the prism that's buried ground. Distant target in, you can see how much things are changing. So now the currents don't want to go through there, they want to go around, right? And that actually is going to require larger charges that are being built on here. So your ability to detect this resistive target might be a little bit superior compared to the conductive target. So you can see all this starts to kind of at least give you some general kind of background on the kinds of things that are important. There's coupling issues, there's geometry, and we can take a look at them and examine them fairly carefully. So the bottom line with the sensitivity is just kind of, again, think about the process. The first is to excite the target. So we need to make sure that we've got currents that are actually going in and being affected by that. The next is that once we've got that, we've got charges on. So we want somehow to have our potential electrodes, as close as possible to this, so that we get a good signal. And if we're confined to the surface, so be it. We can still do this as well as we can. So now if we come back to the survey design, faced with with a question, and the first is like, okay, what's the objective? If we have a 1D Earth, do the sounding. If we've got a 2D Earth, then we're going to have to do some kind of a profiling, but it also has to be a sounding. So it's a sounding profiling mode where we now effectively can build up a pseudo-section. And if we have a 3D solution, I mean, generally we're going to need 3D coverage, and that's going to require experimentation as to kind of planning out what you think you know about the problem and where you should be putting your electrodes. You need to know about what the background conductivity is, or the background resistivity, and also other issues are just sources of noise, power lines, fences, and things like that. So these are all questions that kind of come into play. And again, there's no black brush way of telling like, okay, go out and you do this. It's everything is completely individual. So I think what we're trying to do here is just kind of give you a methodology. So let's suppose you've got a target in a 3D background, and you're really trying to see if you can find this guy, right? So the question is, can we set up an experiment where we can see this? And we have to appeal to numerics in general, especially when you've got topography. There's no ability to do anything that's really easy. So here's our steps. So let's first of all define our geologic model. So we get here, and then we need to assign physical properties to this. That means both to this conductor that you're looking for as well as the background, and then select survey. Decide, okay, I'm going to try current electrodes here and here, and see what I get, and then simulate your data, both with and without the target, and then you get something that looks like this. Without the target, you might have this dashed line. With the target, you've got the red line, and then you look at the difference between these two guys. So that's your signal, right? And then if that's going to be a good datum, then it has to be large enough. So this number here has to be large. If that's, what do we got? So that's maybe 0.2 millivolts. 0.2 millivolts better be well above any kind of a noise floor that you've got. Otherwise, that's kind of swamped. The other thing is generally that this should be a certain percentage of your primary field. So you often think about numbers like anomalous fields being like maybe they need to be at least 2% of the primary or something. Those are the two issues that are really important: the absolute value of that number, as well as sort of the relative strength of that number compared to a primary field. And frankly, that's kind of what you're up against in a general 3D framework. You've just got to build your background from whatever geologic knowledge you have, assign physical properties, decide what it is you're really trying to look for, and hypothesize an experiment, see if your signal that you're measuring is actually sensitive to that target, and if it is, you say, okay, I'm going to go spend some time collect that particular data, and gradually generate your whole survey. So that's sort of like the DC resistivity in a nutshell. So we've kind of talked about the basics, pseudo-sections, bit about sensitivity, survey design, and then the question of what we've learned. I was going to put it in that, but I think I'll do the case history first, and then we'll break for coffee, and then I'll bring the app in, and then we can use that as a way of kind of refreshing our insight about what has gone. So I'd like now to just go over and do a case history. Actually, it's from Mount Isa, which is close to your hearts. So. Who here has been, I don't know, somehow collected with Mount Isa? Oh, more people that do about sewer sections here. Okay, so here's Mount Isa. This was done many years ago with Andrea Rutley. I guess we're pretty we're actually pretty proud of this particular case history, because it was the first use of our 3D DC resistivity and IP inversion code that we had. So it was actually a pretty long time ago. It was like 1998 or 99, something like that. And at that time, 2D inversion was getting pretty common, but 3D was still a little bit on the leading edge. And yeah, we were working with Andrea. She had done some first pass work using our 2D code, and was also using other codes. And, it was just an example that actually came up pretty. So even though it's an old example, it's still, I think, very relevant today. And I was hoping that. Where is she based out of? Is she based out of Perth, or anybody know? Okay. Anyway, I was hoping she might show up today, but we're not sure exactly where she is. Anyway, so we also call this. So there's 7 steps in this that we're going to go through. So use this as an opportunity to kind of go through that 7-step process. So I'm not going to go into a lot of of detail here, but basically, the setup was that could we find a mineralized body that was moderately conductive in a background that has got a lot of volcanics and different kinds of shale units. And in particular, there is a black shale unit that is pretty highly conductive. And so here was a geologic cross-section that was generated, and then the goal was to see if you could do a DC resistivity experiment over this and an IP, and see if you can find it. So the physical properties, is the different geologic units. There's a couple that kind of stand out from the point of view of electrical conductivity. The thing that we're looking for was something called the Mount Novot horizon, which is a highly conducting unit, but not the biggest conductor in the area. That's a breakaway shale, or a black shale. There's a couple of siltstones in here that have moderate conductivity, and they actually host the Mount Novot horizon. And then there's a couple of volcanics that have low conductivity. So that's sort of overview about what one might know about the various rock units and their electrical conductivity. Here's a map of the surface topography. There's not a lot of topography that goes on here, and the structures are thought to be going pretty much north-south, so they're kind of 2D-ish, which is why the 2D inversions produced some interpretable results. The data acquisition are going to done in lines. So there's 10 lines of data that have been collected. So these are all pole-dipole, right? So kind of talked about that. So the current is here, and the potential electrodes here. And then with the current being here, then the potentials are measured along this line all the way out. Then you move the current over one and gradually get build up the pseudo-section. So what we're looking at here, there's 10 lines of data that corresponds to these 10 profiles here. And this is the pseudo-section. So the red here means really conductive. So this is millisiemens per meter. So this is actually 1.4 Siemens per meter as far as apparent conductivity. So that's really big. And then it goes down by about 3 or 4 orders of magnitude. So what do you see here? Well, there's certainly something that's conductive that's coming in here, but that doesn't provide you with an image of the geology. The other thing is that this is a pole-dipole experiment. So the current is always like on kind of one side. So that means, you know, the currents are kind of emanating out. So they're just sort of going in, you know, in kind of one direction. If I was trying to illuminate this part of the region, and I'm just kind of going over with a single current source that looks like this, I'm going to see a certain excitation every time I put the current down. So now you think about charges, right? Okay, I put a current down here, you know, then charges are going to get accumulated in some distribution, and you know, that's going to get measured, right? But I could actually excite the Earth with a different geometry of currents. And I could do that simply in this manner. I could have a dipole pole. In other words, I take the current source, now I put the current on the other side. So I'm going to get a very different excitation of the Earth simply by having multiple sources. And in general, in 3D environments, you excite the body from many different directions. So this is one way of doing that simply here. So you can see how the pseudosections change. So you're still doing stuff on a line, but when I put the current on this side, I've got, you know, just a lot more accentuation of the highly conductive material. Okay, so that's good. Now I've done my experiment. So I've got 10 pseudosections plus the 10 I had before. So I get this 10 and that 10, and those are my data. But it's hard to digest from them, you know, what the geologic structure is. There's only one Earth out there, and our goal now is to, you know, find an Earth model that's at least compatible with all of these data. Convert them. Now, to do that, okay, so this is a 3D inversion. So now, I mean, I think these things are now pretty standard, right? You take a mathematical cube and you know, divide it into a whole bunch of little prisms. Each prism has got its own electrical conductivity value. You just adjust those to so that you get something that's geologically smooth or reasonable, and at the same time you fit the data. So that's what we were doing back in the 2D inversion. Do the same in the 3D. In fact, all of the inversion algorithms that we work in that same way. So take the Earth, parameterize it somehow, 1D, 2D, 3D, and then you solve an inverse problem using kind of a Gaussian technique, and end up with a final solution that has got you know, some degree of smoothness, has got geologic information that's built into it. You know, hopefully is useful. So this is what we've got. So it's a cube. Actually, it's not hugely big. I mean, it's only, this is about 500,000 cells. These days, we can solve things that are actually much bigger. And what we're going to see here, the red is conductive, the blue is resistive. And this is the finite cube. There's 500,000 numbers in here. And then we're just going to view that cube in a number of different ways. Kind of slice into and out. And then I'm going to slice top to bottom. And then I'm also going to rotate. So you can see we're kind of slicing through. The big thing that's of note is that red unit to the right. There's a little guy coming up here, notice in the middle. So there's that guy here. He'll turn out to be interesting. Oopsie, come back here. So now we're going to just slice through. So you can see the big, long, high conductive region. So what's happening here is that as we've rotated around, we've successively changed the isosurface critical threshold, so that in the end, you're seeing only the most conductive unit. So that's probably enough. So let me just. So there's a conductor in here, and there's this great big conductor in here. And then again, you can see it here and as well as here. But this is that black shale unit. And now as it's rotating around, we're changing the isosurface so that we're progressively seeing higher. The only thing that's being exhibited is just like the really high conductivity. And then another image of that is over here. So I mean, we were absolutely amazed, and so was Andrea, I think, when we got this, because people had been trying to interpret pseudosections 3D, and even though there was a lot of information that could be obtained with the 2D, the 3D results definitely added a lot. Yeah, that was a success story. But now we kind of come back to the synthesis. So, okay, so that takes us to the interpretation. Like we've got our 3D modeler, we've done the processing, and now we really want to kind of sort of carry out this interpretation. And this major conductor that we've got in here, that's just a black shale unit. There are some indications of a moderate conductor. Unfortunately, this black shale unit here is totally uninteresting from a mineralogical perspective. And so that particular experiment, as far as DC resistivity current, was not overly diagnostic in defining the mineralization. What we're going to see is that the mineralization is actually more responsive, or I think it's more diagnostic, is chargeability, which is kind of related to conductivity. That actually is going to be the last topic that we'll do. So we take this case history. This is as far as we got with the DC resistivity part of that survey. But now we're actually going to use this information in that DC resistivity result, and we'll use that this afternoon to look at the chargeability or induced polarization IP response, and see where that leads us as far as actually trying to find that mineralized body. So that's kind of where we are. We've now done a case history. Before we break for coffee, I just want to do one thing, because we haven't talked very much about the effects of background resistivity. So let's just think again about this. So we've got, here's our kind of canonical model. We've got a conductor in here, put currents in through here. They get deflected by the sphere. And we did an apparent resistivity over here, and we got 430 ohm meters. So, you know, we're kind of sensitive to this, this conductor body. Okay? The question really is like, if let's suppose I put a layer on here, and I actually make that layer either conductive or resistive. And the question is, you know, what's going to happen? So we had looked a little bit at this before. So if you have a conductive layer, the currents kind of get channeled in. In this case, we're going to put a resistive layer on here. So if I have even a thin resistor, then what would you expect that to do to the currents? So let's suppose I take my sphere here, and now what I'm going to do is put in a thin resistive plate. It's just up in here, so it's just going to be just a bit above that. So if I put a thin resistor in this case, expect to happen. Yeah, so I can't drive current through a big. So if I try to put current through, it's not going to go through. So a resistor is basically like you know, an impediment for any current to cross, and a thin region, but that's very, very resistive, I'm simply not going to be able to drive current across there. And that's what this image is showing here, is that if I have a resistor that's like this, all the current is actually sitting now above that resistive contact, and the current is kind of flowing through there. And if I did my apparent resistivity here, so if I did the same thing, I would actually get an apparent resistivity of 1600 ohm meters. So not see my sphere underneath here. I've just got a resistive value that's huge. So there's no way I could sphere. So that's a really important thing that you know, you kind of get like, okay, I've got a good method. I can go ahead. I've just seen a DC resistivity, find a conductive sphere and a background. But if I have a background that has, you know, even a fairly thin but highly resistive value to it, like if you put down a piece of, you know, extremely resistive polyethylene, you know, which could be really thin, that can be enough to prevent any current from getting through. In fact, that's one of the things that they use in these liners for tailing ponds or something. They'll put down a you know, a barrier. Often that barrier is just really kind of a resistive you know, polyethylene of some sort, and yeah, that keeps the currents inside. And then it's only when you've got a hole in that liner that you get fluids and that could be then used to maybe sort of trace where the weaknesses in the liner. So this is what happens. So you can see the currents are basically confined to the top, and our apparent resistivity is actually higher than you know, than our background of 500 ohm meters. And just to kind of help explain this number here, if we do the experiment again and then compute what so now we're going to take the sphere out. Okay, so Now we're going to do the same experiment. Take the sphere out, so there's no distortion under here. But nothing really changes. You still get an apparent resistivity of about the same amount, which means that you're simply not seeing that sphere at all. Okay, so that happens with a resistive background. What's going to happen if I change this guy here and make him a big conductor? See any of this? Regis? Pardon me? Oh, no. Okay, sorry. Go through the conductor layer. Yeah, so it's just the same now. It should get channeled through. So if I have a conductive layer here, now you can see what the currents do. They go down, go through the conductive layer, and then back up. And again, if I take that sphere away, then I don't change anything. So the apparent resistivity here is low. It's 47 ohm meters, but it's not low because there's a conducting sphere there. It's just simply low because you've got a layer of really high current. So the takeaway home or message here is that for a DC resistivity experiment, the background host configuration can be extremely important, especially if you've got highly conducting or highly resistive units that are going through. So that's a pretty good place to stop and have a break. So we'll have coffee. We'll come back and show you an app, and then we'll start with EM fundamentals. Good. Just say, what's up? Anyway, as long as no, that's all we used was those two sections. We didn't make sure. So yeah. So you just have to here. This one. But you make cells that straddle the whole. No, you don't need two sections. So you just need. So even though I'm measuring here, I can still be sensitive to something that's happening over here. Right? So if I've got data line here and data line here, I might actually have No, that's all done by so we have unique cells very small. So that means that you don't need to structure. We're just trying to find a distribution. That one? Yes. Have you been converted? Yes. What part? Yeah, so if you're going to do, would you do it parametrically, or would you have done it just by taking all the volumes here, so yeah, so that's all we do. So I don't need to have data everywhere. Just like, okay, that's really cool. Could be completely. Yeah. Yes, the fact that I've not thought in terms of data sets. It's just data. Oh, yeah, exactly.
It's pretty good. It's pretty simple. It's not as like bonds shares coming up. Basically, that kind of happens. So one has to be
Mike, are you going to be here tomorrow too?
Yeah.
All right, can I ask people to take a seat? Oh, I need the. They're supposed to have something.
But that'll then sort of mess up the apps.
Nope.
Oh, yeah, no, sorry. I want to do that.
Can't see. I take. Maybe I should just go back to this. I don't want to screw up the apps, but I want to show you. See.
So all you have to do is just create. So just click the green button. So all you want to do is just go big.
Okay. Okay, so on our main resource is something called EM GeoSci. So if you just went to this index, GeoSci.xyz, then you'd be faced with this particular window that we have here. Quite a lot of material on here. We've got sort of introductory material just to kind of set the scenes. We've got sort of physical properties that you can take a look at, that background information about what the various physical properties are, how they're measured. there's Maxwell's equations, there's fundamentals with talk about basic equations, solutions, plane waves, and homogeneous media, the kind of stuff that you'd see in a lot of books. There's something called static, which is electromagnetics at zero frequency. That's what the DC resistivity is. Frequency domain, time domain, and so that's sort of the background to things. And then there's geophysical surveys, DC resistivity survey, induced polarization, airborne, frequency domain, time domain, magnetotellurics, etc. Just the background of each of these, and we've tried to present them in a sort of a uniform framework so that if we did DC resistivity, for instance, each one of them is kind of listed in this way. Physics, well, what's the basic physics? What's the data, interpretation, practical consideration? So these things have, they're a way of kind of presenting each of the different types of surveys in kind of a uniform manner, and you're always kind of connected to fundamentals. And then there's case histories. Here's a whole set of case histories that do, actually, there's one called Buprenon, which perhaps people in Australia know because it's got to do with the Murray River. There's everything from looking for minerals to looking for water resources, and each of these is presented in a 7-step framework. So it's really kind of well organized, and the other thing that we like about this is that we're trying to make everything kind of connected. So we've got these fundamentals in one aspect, Maxwell 1, 2, frequency domain, time domain. And then we've got the geophysical surveys, and then we've got the case histories. So within the context of using the resource, you've got two opportunities. You can either start, kind of work your way through fundamentals and then surveys and then to case histories. Or the way in which we see a lot of people using this and making use of it is that there's a problem, and there's a case history that's associated with this problem. So they start reading this summary of the case history. In general, you can access a formative paper that was associated with this, so that's there. And then the idea is to connect as you're reading the elements that are important. Like if the first thing is DC resistivity or electrical conductivity, it's all hyperlinked. So you can hyperlink back and you find, oh, that's what that means, and then kind of continue on. So the goal is to kind of connect all of this stuff together so that you can kind of go through and work with your case history, understand the data, understand how it could be processed, understand all the things, and at the same time kind of keep your eye on the prize here. So that's the goal. I'm not going to say any more than that. You're invited to explore. We can talk more about that later. The thing that I wanted to do now, the very first thing that you see up there, so it's apps, and so if you click on that, you'll be faced with this particular page here, and this is your gateway into a whole bunch of notebooks. So Lindsay's going to kind of describe that whole process and whether you're going to use Azure or what your connection is going to be. So she'll take you that. We'll do that just before we break for coffee. What I'd like to do is to look at one of the notebooks. Just a second here. I can look at a notebook here, which is it's kind of related to the material that we did this morning. I think we can kind of use it to sort of help us with it. So this is all written in Python. These Jupyter notebooks. And the purpose of this one is to just explore how, if you had a circular target or a cylindrical target in here, how the DC resistivity experiment would work. So we've got a couple of things that are involved here. We've got current electrodes that are sitting here. So here's an A electrode, a B electrode, M, and N. We've got a target, so that'll have a certain radius. It'll have you'll be able to put this target at various places. You've got a background resistivity and a resistivity of your target. So the notebook is designed so that you've got enough information here to kind of help you play around with things and to really define all of the things that are of interest. And then there's slider bars here that you can adjust to experiment with, right? So here's the ABMN, here's our radius of the sphere, here's the location, X and Z of the sphere, and row 1 and row 2. So it's very simple. But good. So what you're at this point here, the background resistivity is 500 ohm meters, as well as the sphere being 500 ohm meters. And here's the potentials that you have. So basically, you've got the potentials for a house piece. Okay, so let's try to simulate this kind of experiment. So I don't know. Let's suppose we're looking for a tunnel. Right, so somebody comes up, and actually I've had so many people do this. They come up and say, "Well, can I use DC resistivity to find a tunnel?" It's like, well, maybe, maybe not. Kind of depends. So let's try to design something and just play around a little bit and see how we can not only help answer that question, but also to take a look at some of the things that we looked at this morning. Okay, so what's the first thing? Somebody says, "Well, can we find a tunnel?" What's the first thing that we need? Okay, yeah, so let's do a background resistivity. It's currently at 500. Leave it like that or move on. Pardon me?
The tunnel itself would be sort of like infinite resistance.
Well, yeah, so that's an interesting thing. So somebody says that a tunnel, and we're trying to decide on the resistivity of the tunnel. Anybody here has looked for tunnels? Yeah.
It could be filled with water, or so you gotta, if you know that, then you can put that in as well.
Perfect. Yeah. So we've got a tunnel. We've got to decide what it's filled. If it's air, it's really resistive. If it's filled with brine, it's really conductive. So it could be either. What would you like? Resistive tunnel or conductive tunnel? Conductive tunnel, that's what you look. Okay, so we've got a little bit of a limitation here, minus 40 to 40 meters. So let's build a tunnel. Want to decide some dimensions?
Maybe 5 meters in radius.
Okay, so let's go back here. So here was our radius. Let's set 10, so we could go back to 5. Okay, so that's 5 meters. And yeah, so we're going to make it conductive. What would you like for resistivity? 10, good number. Okay, so 10. And we also need to place this tunnel someplace. How deep should we make it? 20. Ooh, okay. All right. Ooh, that's off my scale. Okay. That's right. That's okay. There it is. There's our tunnel, 20 meters. Our A and B electrode out here at minus 30 and 30. Okay. Good. So let's, that's our geometry, and here's our electrodes. And now we can view things, right? So this is the really good thing. We can take a look at all kinds of stuff. I was showing you the currents this morning. Currents are really nice to look at. Okay, so let's look at the currents. That's not bad, right? I mean, you can definitely see that there's some effect there. So that's good. And yeah, so we've got something that's happening up there. And now if we looked at, now you could look at all kinds of things. Those are the total currents. You could look at what are called the primary currents. So that's going to be the, let's see, if I looked at the primary currents, that's the currents without the body in. So that would look like that. So now you see there's no distortion. You put the body in, you get the distortion. I could also just look at the secondary currents. And so you notice how these kind of are like dipoles? It's like we've got a current that kind of goes out like this and like that. So it's like a little electric dipole underneath there as far as the currents are concerned. And do we see this? Do we see this? Well, actually, the background was maybe 500 ohmmeters, and you see there's an apparent resistivity. It is actually low, lower than 500. So you're seeing it. So that's actually good. Okay, what about the charges? Okay, so I talked a lot about charges. Let's suppose we wanted to look at the charges. So now I've got this system up here, and I'm going to press the charge. And there's my charges. Here's my scale. Right. What happened? Anybody got any insight as to that is a correct display of the charges? Not quite what I was showing you earlier.
Is it not enough potential across that volume to differentiate, to make the charges?
It's not exactly, kind of getting close. These are really some big numbers, but you have to remember, okay, when I put a current in the ground, I don't need it. Like, I don't even need a generator. I can use a car battery, right? Sometimes they do. When you think about a car battery, and you hook this up to 2 wires and put it in. What's happening at the A electrode? Well, yeah, so you've got a battery, right? You know, the positive end of the battery, the negative end, and charges that are going up. If I hook that positive end up to the ground, it's just like, okay, there's a big charge here. This one, you plug this battery in, you've got a big positive charge, got a big negative charge, and that's actually swamping the system. But if we now take away that, the effect of that kind of primary charge, and we look at the secondary, now we see, okay, that's more like what we were expecting. So now we've got secondary charges. These are built up on here because remember the currents had to go through. So we went from resistive to conductive, and that actually gave us a negative charge there and a positive charge on the other side as we're going from a conductor to a resistor. So these guys here, those are our charges. And now we can look at the potential. So here's that's just the secondary electric potential from here, but that's the signal that we're trying to get. And we'd be measuring that up here. But again, once you go back to look at the charges, this is kind of insightful, right? Because you just remember, like, okay, well, it's Coulomb's law. So if I put in an electrode here, I'd be really sensitive to these positive charges. If I put an electrode here, right? So you can start to kind of figure out the relationship between the currents that are going through, the charges that are being built up, and the data that you're going to collect. You can also experiment with the different kinds of configurations. Well, actually, first of all, let's suppose we change the tunnel. So you had a tunnel. Okay. Now we'll come back. You are going to make it resistive. So how resistive should we make it? And then also what's going to happen? So if I made this, so this is kind of what we got right now. It's a conductive tunnel. If I make it a resistive tunnel, what am I going to expect? Pardon me? Yeah, we can hope for that. That's right. So I might expect these guys would change sign. Because as I'm going from a resistive to a conductive media, I'm going to get a negative charge. Go conductive to resistive, I get a positive charge. So if I change that resistivity, so instead of making it 10, I'll make it 8. And there. So we've flipped things around, and your apparent resistivity, you're right, so now it's 536. So that's what's happening. Okay. Let's just do one more little thing. I don't want to spend too long. You could use a lot of time on these things, but kind of fun to play with. But we'll go back. We can leave it as a resistive tunnel. That's fine. Let's change it. So we have a dipole. Sometimes things are interesting just by looking at a pole, a single electrode. Let me just move this guy up just a little bit. Kind of accentuates things a bit more. Yeah, so I've moved it up, and if we look at the currents, so the primary currents. So there's our primary currents, right? So they're behaving exactly like you think it's uniform space, and they're just kind of radiating upwards. And now I'm going to try to put a cylinder in there. And if I do that, and if I look at the total charge, or the total currents, so you can see here what's happening, right? So that's a resistor, and the currents are kind of flowing around. Good. And now when I sort of look at that system, the reason that those currents are flowing around is I got charges built up, so I can look at the charge. And you see it's like this. Okay, so I've got this guy, positive charge here, negative charge here, and if I look at the potential that's measured there and convert that to an apparent resistivity, I've got 532 ohm meters. So it's above the half space. So what's going to happen is I change M. So let's suppose I just move M. I think this is kind of interesting. So if I put my potential electrode here, I actually get that the apparent resistivity is 500 ohm meters. Right? So it's sitting right here. There's a little bit more positive charge there, distribution, and negative charge here. But you know, you add up the effects of all the charges. So you're sitting here, and this particular value has effectively a null value. It doesn't have any. It just gives you an apparent resistivity that's equal to the background. And if I move it out like this, here it's actually less than 500. Okay, so people sometimes get confused between okay, I've got a resistor. It should always, my apparent resistivity should always be larger than my background. But that's not the case. And the reason you can see easily now that it's not the case is that, okay, well here, I'm actually closer to these negative charges than the positive charges. So there's a lot of strength of positive charges here, but I'm physically closer to here. So I'm more sensitive to those guys. Those are negative. That's going to decrease my potential, and my apparent resistivity is decreased. Okay, and one final thing is just to watch. If I can get A on here at the same time. Okay, so watch. I'm going to keep the charges on. About excitation. I'm going to keep the charge plate on. I'm just going to move the A electrode here. And what do you expect is going to happen if I move this? Anybody? Is it Roman? Yes. Yeah. What's going to happen? So the thought is that somehow the charges are going to rotate. So let's just see if that happens. Sitting up there. So you can see now there's actually, it's pretty sort of smaller concentration of positive charges. So the great thing about this is that I think it just makes this whole process of thinking about exciting the target, it just kind of clears it up. It's like, okay, I get it, right? So, and you can also see why each way in which you excite the target might actually give you, a different set of responses. So ultimately, what you want to be able to do is to excite this target from as many directions as possible and measure a lot of data that's associated with that. And then, yeah, kind of good to go. Okay. Okay, moving along. Okay, so now we've done the DC resistivity. I want to move on to sort of fundamentals of EM. So what's our motivation? Well, DC resistivity, maybe you got large areas to be covered, 100 kilometers by 100 kilometers. That's big. Or maybe we saw this case where we had the resistive layer in here that was basically shielding things. Sometimes you simply have rugged terrain. It's hard, you put a current electrode in, but you can't get current in the ground. So there are times that DC resistivity is great. There's other times like, okay, it's making it a bit difficult to work with. So we're going to appeal in these cases to electromagnetics, and I want to go through some of the basics with amperes and Faraday's law, a circuit model for EM induction. We're going to look at frequency and time, and we're going to look at spheres in a homogeneous space and energy losses. So what's the basic experiment? So let's suppose we've got a transmitter and a receiver. So we've got a transmitter in here, receiver, and that's going to produce a primary magnetic field transmitter. And those magnetic fields, if they're time varying, are going to generate currents that are in a conductive body. And those currents are going to give rise to magnetic fields of their own that could be measured in a transmitter. So those are the basic steps. And now we're just going to walk through each one of them and get a complete understanding of, okay, how do they all kind of fit together? So first of all, let's just go back to the beginning. Let's think about our transmitter. So here's our transmitter. In this kind of a survey, it's just a loop of wire. So it's just a little loop of wire, and that's going to give rise to a magnetic field that looks like that. The current that's in the wire could either have a waveform that looks like this, and we're going to generally refer to that as transient or time domain waveform, or it could be harmonic and just have a particular frequency. So our basic equations are again back to Maxwell. And now I can spend a couple of minutes talking about these things. So the first one that we've got here is Faraday's law. And that says if I've got a time rate of change of B, which is the magnetic flux, that's going to give me an electric field. But there's a curl operator here. So it's kind of like a time-varying magnetic field is going to give me, some kind of a curl or a circular electric field that's associated. Then we got Ampere's law that basically says, oh, if I have a current, so J is a current density, then that is going to give me a magnetic field. So, but again, it's kind of a curl. So, a J gives me a circular magnetic field. And then I've got this constitutive relationship here, Ohm's law, J is equal to sigma. So these are the equations in the time domain. These are the equations in the frequency domain. So let's look a little bit first at Ampere's law, which talks about the relationship between currents and magnetic fields. You've all seen this guy many times. You're back in grade 7 or something like that. Take a circular, you're going to take a wire, right? And you've got a current that's going through the wire. And then you say, oh, what's the magnetic field that's going around with that? And it's a circular magnetic field that is going around the wire, and its value is given by this. If I take that wire and turn it around on itself so that I make a loop, then on each place there's kind of like a right-hand rule, but at the end of the day, it's looking like a magnetic field that looks like that. In fact, it's like that of a dipole. If I put a magnetic dipole there, and this is the equation for it. The strength of that magnetic dipole is given by the product of the current and the area. So a wire loop gives me a magnetic field that is exactly like that of a bar magnet. So that's our Ampere's law. Just a sec. Now we have Faraday's law. So Faraday's law looks like this. It says time rate of change of magnetic flux gives rise to an electric field, and then that's coupled with Ohm's law given by here. So how do we recognize this? Well, this again you've seen before. So here's our experimental setup. Every year has probably done this experiment. You got a loop. There's a coil of wire here, and you got a magnet north south, and it's all connected to a voltmeter, and there's a current that can go through here, and light. If the current goes through, makes a light bulb go on, right? So is to, first of all, look at what's happening at steady state. So it's a steady state. We've got a magnet. Here's its magnetic field lines, right? So these are the lines of B. They're permeating the coil, no problem. But there's nothing that is changing, so everything is static. The quantity that's important here is the relationship between this B field and the conductor. And the essential element is something called magnetic flux. So that's the integral of B times the normal of this loop over the area of the area of the coil. So at this situation here, the flux is constant. There's no time variation. So there's no EMF or voltage that's induced in the system. So everything is, nothing's happening. But now I'm going to move so I push the magnet in. So that means that the flux is increasing. And now that means that I've got a voltage in here that is negative because of this minus sign. And I've got, so I now have a current. So if I've got a voltage through a circuit, there's going to be a current. And so we can see that the light's on and the current is negative. So it's going around one way. If I do the opposite and I pull this back, now my flux is decreasing. So I'm going to get a positive voltage in here, again, some kind of current, and the light bulb is going to go on. Okay, so that's the relationship, and the important part here is that so this time rate of change of flux gives rise to a voltage or electric field inside here. The other thing was this minus sign, which is due to Lenz's law. And basically what that says is that the current that is induced is in such a way as to oppose any of the changes in the magnetic field. So the Earth, well, natural systems tend to like kind of quiescence. They don't want to be changed. So if you impose a time varying flux on something, there's going to be a reaction to that's set up to oppose that. So that's where the minus sign comes in. So we have a couple of apps. We've got two of them. One for a transmitter which is harmonic, and one for which it's transient. So I'll show you that in just a second. Take you first of all through what's expected for the transient pulse. So in a transient, we're going to have a current that is on, and then is going to get turned off. We have let's see what the next slide is. Yeah, that's okay. So here's, maybe I'll just go back here a little bit. So our two coil apps. There's going to be a transmitter that is giving rise to a primary field. So that's going to be this outer coil here, and that's going to give you a primary field. And then there's going to be, for a target, we're going to have an inner loop here, which is going to be sitting in, it can be at various relationships to the primary field. So it's basically a time-varying magnetic field that is associated with this primary group and impacting on, trying to generate currents in the sky here. So in time domain, the primary field is in this outer loop. It's going to change and cause currents to flow in this inner loop. Primary current is going to be on and then off. And then the magnetic flux is going to be similar. It's going to be in that same, because the flux is completely in concert with the current.
The time rate of change of flux, however, is going to be impulsive. The moment that I turn the current off, the magnetic field disappears. So dV/dt is a delta function. And that gives rise to an initial voltage in a circuit. So we can represent our whole system as a circuit where we've got a resistor and an inductor and a voltage. So the EMF is applied by this changing flux that gives rise to a current that goes through here. And because there's both an inductor and a resistor, that current will gradually decay. So the nature of the secondary current is some constant value times e to the minus t upon tau, where tau is a relaxation constant being equal to L, the self-inductance system, divided by R. So that's basically the two-coil example that is for a transient signal. And then the response function for that is that we've got a step-off current, looks like this. So here we have our circuit model. Tau is equal to L upon R, and the response function is just really how that current changes as a function of time. And if tau is really long, it takes a very long time to constant. We plotted things in terms of two ways. One is, here's the response function as a function of linear time, and so that's going to like this. If I plot it as on a linear plot, keep losing this, on a linear plot, it'll look like this. So on a log linear, we've got straight lines. On a linear plot, we've got things that are just really heavily exponentially decaying. So that's our response function for a transient signal. So what happens if the current, instead of being transient like this, actually becomes sinusoidal? So if we have if we go back to our two-coil example here, and now we think about our primary current. So now our current is just sinusoidal. It's a cosine omega t. If the primary current is harmonic with a particular frequency, then anything else, secondary currents, must also be harmonic with that same frequency. And the only thing that can happen is that it could have a different amplitude, and it could be somehow phase shifted. So what we will see is that we've got a primary current that looks like this, and a secondary current that has got this line here. So it's got the same frequency, but it's out of phase, so it's got a different amplitude, and it's out of phase by a certain amount called epsilon. So we could write that in here so that our secondary field looks like this, but then just from basic trigonometry, we can expand this quantity here to write it like this and this, and so two terms. This term here depends upon cosine omega t, so that kind of looks like the in-phase part. And this part depends on sine omega t, so we call that the out-of-phase part of the quadrature, or the imaginary part. But basically, all that's happening here is that we've got a harmonic current in here. It generates a harmonic current inside here. That current has got its own amplitude, and it's phase shifted. And we can take this secondary current that we've got here, and we can write out what it is for the in-phase part here, and the out-of-phase part out here. The phase lag is given by this expression here, which depends upon omega L upon R, called the induction number. So our phase lag has got pi by 2, that was the minus sign, and then this induction. So what is the response function look like for a frequency domain system? We plot our response as a function of induction number. Then we get an in-phase part that looks like this, and an out-of-phase part that looks like this. So this plot is kind of characteristic. You're going to see this a lot. It's something that, yeah, is plotted in virtually every book. And at very low frequencies, we see that the real part is very small compared to the quadrature. At very high frequencies, the real part is very large compared to the quadrature. So in summary, the thing that I wanted to comment here is that there's really not very much difference between frequency and time. In time domain, we've got let's say a step off. We get currents that are induced in here, and they've just got this exponential decay. In the frequency domain, we've got harmonic currents, and they just partition themselves into something that's in phase and out of phase with that primary current. So maybe that's a good enough place to. Let's do this one first. Okay, so here's a lab that you can play with. So the parameter description, there's a yeah. So there's two loops here. There's a transmitter, and then there's a receiver. So the receiver could be at any depth, any angle that it's got. So it's got a, you can rotate it, you can put it at any particular depth. Both of them can have their own radiuses or radii, and you can specify the resistance and the self-inductance of this target here, which are kind of circuit parameters. You can specify the frequency. Okay, so let's just take a look at this guy. So we've got an initial current of 1 in the transmitter, and the frequency is log frequency, so that's 1,000 hertz, and we've got receiver loop down here that is just 8 meters beneath the transmitter. So this receiver is actually kind of lined pretty nicely with that. We'll talk about that in a second. So it's kind of the whole idea of coupling. We want to get magnetic flux from the primary field that's going through there. And when we look to see what is what we have happening here, so the dark line is the primary field, and the green line is the secondary currents that we've got, and we see that the amplitude of that is really small, because our response function, we happen to be sitting here. Here's the response function that we've got, but our frequency that we have is really low. So we're at too low a frequency to really see very much, but if I change that frequency to be maybe more like 10 to the 5th, so this 100,000 hertz. So now you see that with respect to our response function, we're sitting up in here. The secondary currents have this variation here. They're in green. And I can take that and split that into an in-phase and a quadrature phase part, so that this green line then splits into a red, which is the quadrature, and a blue that is the in-phase. And you notice that the quadrature is a little bit higher than the in-phase. And that's actually, you can see that from here, that is what it should be. The dashed line is a little bit above the solid. So the kind of take-home thing that I just wanted to illustrate here with this is that we have a primary field. It generates a current in the loop. That current in the loop can be kind of in phase and out of phase, or it's part that's in phase, part that's out of phase. And so we get two of these currents there. Okay, so we've got sort of response functions and some general idea about how this is going to work. Let's now kind of look at the secondary magnetic field. So we've now got currents that are built up, and we've got Ampere's law that if we have currents in here, should give rise to a magnetic field. And then how are we going to measure these guys, and what are we going to measure? Well, we have options. You can have B field receivers, so they could be flux gate magnetometers, and they could measure fields in multiple directions. So you could have 3 components. We could also have coils that measure dB/dt, and they could also be 3 components. So all of these exist, and yeah, various systems use various ones. I talked a bit about coupling very briefly. This diagram talks about it a bit more, and that is that in receiving the signal, the coupling between the transmitter and receiver is really important. What we mean by that, suppose that here is your transmitter. If I have a coil that's sitting down in here, then I've got this kind of maximum amount of flux that's going through. In other words, I'm really well coupled with that primary field. However, I took this coil, if I moved it up to here, now the magnetic field lines are going like this. There's nothing really that's crossing the plane of that loop, and hence I've got really poor coupling. So here's null coupled. If I'm sitting out here, my magnetic field is coming in like this. So what's very important from the point of view of your sensor is how well you're actually coupled with the fields. This diagram actually works both for a transmitter and a target loop. So this could be the transmitter in your plane and your target loop. It also works for the currents that are in the target, that have been induced in the target, and your whatever receiver you've got. So there's 2 sets of, or there's 2 places that coupling comes in. So if we put all of that together, we've kind of we can make a circuit model that has got all of the elements. So we've got a transmitter, an object, and a receiver. So for the transmitter, we can replace that by a coil. For the target, we're going to replace that by another coil. And for a receiver, we can replace that by another coil. So this is, I think the first time I saw that was in a book by Grant and West, or Telford has also got this. And it's very old representation, but it works really well. So we've got 3 loops, and these quantities M here are called the mutual coupling effect. So they just depend on what I showed in the previous diagram with respect to how one coil is kind of coupled with the fields of another. So this one is M12, so that tells you about the coupling between the loop and the target, M23, target and the receiver, and M13 this way. These coupling coefficients depend purely on geometry. So if you know that, then you can evaluate that. So now I think we're in a shape to put everything together. And that is that suppose that we're interested in like the ratio of the secondary field that's measured receiver to the primary. Okay, so the secondary field, first of all, we've got to get to the transmitter to the target. So that's M12. Second, to the target to the receiver, it's M23. And that is compared to the primary field, which goes from here to here. That's this M13. So that kind of does, all this stuff out here is the geometry. The field in here carries with it the response function. So now we've got the response function of the system, which is written like this, where alpha is that induction number, omega L upon R, and the response function looks like this. So this actually allows you to do a lot of kind of interesting things with respect to understanding how you're able to illuminate this and to decide what your responses are actually going to look like as far as being in the real or the imaginary part. So let's just look at this now as let's suppose we've got a conductor in a resistive earth, and we've got a loop system. This is actually fairly common. We've got a transmitter. Has anybody heard of an EM31? Yeah, a few people. So it's basically a long boom. There's a transmitter at one end, a receiver at the other. It's about 3 meters long, operates at about 10,000 hertz. And you're just going to go over this particular object here. And as you go over it, there's all changes of mutual coupling as the transmitter and the receiver change relative orientations with like this. And the signal that you get is characteristic. It looks like this. So if the induction number is equal to 1, the in phase and the quadrature phase are exactly overlapping. So this guy is here. And the response would look like this. If the induction number was less, in other words, I had lower frequency, then now I'm actually moving down this way on the response curve. The imaginary part should be greater than the real, and the signature that I would get would look something like this. And if I went the other way, I'm now over here, so the real part's larger than the imaginary, and it would look like this. So the bottom line is that the character of the signal is actually determined a lot by just all this mutual coupling stuff. And the amplitudes and the partitionings are dependent upon what the induction number is. So, and if we return to the time domain, the transient, we actually have the same kind of thing. So again, you have that same kind of character because that's all the mutual coupling. As time changes, at the very earliest time, you get the largest response. And at later times, the character stays the same, but the amplitudes continue to decrease. So the response function, you remember, was just on a log linear plot, something like this. I mean, just as you go later and later in time, the amplitudes decrease, but it doesn't change the character. So just to recap what we learned, we've got some basics of the induction. We know about response functions, mutual coupling, and we see a little bit for data for frequency or time domain systems. And also then we've got a circuit model that provides some representative results. But the question is it useful for geologic targets? So here's a numerical experiment. Let's take that sphere in a resistive background. So here is our circuit. Here's our circuit model for the sphere, and it's got a response function that looks like this. If we now take that sphere, make it 30 meters in radius, and highly conductive, and solve that numerically with a we'll call a silk, we'll talk about that in a sec, then the results that you get out look like this. In other words, the character that we got here and the numbers are pretty representative of the circuit model. So that's kind of a nice grounding formation, because it means like, okay, if I see something with the simple circuit model, that's going to be a pretty good reflection of what's there. So that code has been developed and is also freely available. It's a great code. Actually, it allows a large number of different kinds of examples to be done. It's built on CivPay, and Lindsay has just been a lead author on publishing how this actually works and making it available as far as open source. And there's, I say a lot of flexibility in it, because it's a cylindrical code, so anything that you can manage that is cylindrically symmetric can be simulated on this, and that includes both conductive and magnetic objects. So we've got a few things, but there's a couple of things that we haven't yet talked about, and one is how to get what happens to the energy from the transmitter as it's getting to the target, and the other is getting back from the target to the receiver. So that brings back to the next thing, like, okay, how do these EM fields behave in a conductive background? So here's our Maxwell's equations. These are our first order equations. There's the constitutive relationships. We can combine these into second order equations. And this is the full kind of vector Helmholtz equation that governs Maxwell's equations. It's got a number of terms. It's got Laplacian. And then it's got this term here, which is a diffusion term. And it's got another wave here, or term, which is a wave propagation term. If this term is, if this term is large compared to the diffusion term, then we're kind of in that GPR regime. If it's small, then we're in what's called a quasi-static. So we can take this and we can do its Fourier transform and write in frequency domain something that looks like this, where k squared is your wave number, and that's that representation. If we look at this equation here, and this writes it out a little bit better. So here's your wave number. If this term is large compared to here, it's called a quasi. You can neglect this wave propagation term, and you have what's called a quasi-static approximation. And under those conditions, then we're effectively neglecting the displacement current. The wave number takes on a simplified form like this, where the alpha and the beta have this quantity here. So only get frequency, mu, permeability, sigma, conductivity. Putting that into this equation gives us a solution for what's called a plane wave. And it's got two terms. It's got an attenuation term here, so it's e to the minus alpha z. And then it's got a propagation term. So this term comes into the phase. The attenuation term is the one that's really important. And it gives rise to something called the skin depth. So what we're interested in here is as things propagate in depth, then it's going to continue to decay. So it decays as a function of depth with something that looks like this, an exponential. The point that is usually taken is at what point has the field decayed to 1 upon E of its value? And that's listed as the skin depth. And it's given by this particular formula here. So this is actually a really important formula from the point of view of frequency domain, because it tells you how far in does a wave penetrate before it loses 1 upon E of its value, about 30%. And so we'll use this equation a lot. So now if we look at in homogeneous media in time, okay, we have a time domain for in quasi-static solution for that is given by this. What we're looking at here is the amplitude of the wave at a particular time in the Earth. So the you can see that there's if the idea is you turn the you turn an impulse on into the Earth, and it propagates in, and it's got at a particular time, it's got a particular peak. If you're at a particular depth, there'll be a particular time at which something will come across as a peak. In other words, if marks the impulse and sort of sets an impulse off, that impulse initially doesn't. I don't see it, right? But as a function of time, that wave propagates through at this particular time, 0.02 milliseconds. It's a maximum, and then it decays. It decays away. So that kind of tells you what happens if you're standing at a particular point and the wave comes through. The other is that if you looked at a snapshot of the Earth at a particular time, then the question is, okay, where's the peak? And we can define kind of where that peak, and that defines something called diffusion distance. So this peak, okay, kind of arrives at a time, for a particular time t, at a particular conductivity and mu. This sort of distinguishes when where that peak is. And as a function of time, this thing continues to go down at greater depth, and that means that for greater depth, for greater times, you see deeper, shallower times, or earlier times, you see less deep. So there's a plane wave app. We won't do that, but effectively what that allows you to do is to initiate an impulse of plane wave and just watch how it propagates as a function of time. So you can set yourself at a particular location and see how the wave propagates by, or you can take a snapshot at any particular time and see what the amplitude of that impulse wave is. Okay, so just as we're doing in DC resistivity, we're looking at the effects of background, so now we want to do that again. So let's take our transmitter, and now we've got to get energy to the target, and then energy from the target back to our receiver. So all of that now means that we're going to be subject in the time domain to diffusive energy losses, as well as in the frequency. We've got this skin depth problem. So let's just take a look to see what happens here and how the effects of the background conductivity alter things. So here's our sphere. So we got a homogeneous background, 10 to the minus 8 C/3. So effectively, we're kind of out in free space. And if we look at a time of 10 to the minus 5 seconds, then the current densities are here, right? So these are the high values of the current densities. So you can see it kind of illuminates the sphere. Yeah, so maybe the first question that I have is, it's kind of interesting that the currents are just kind of illuminating the outside of the sphere. If you thought about energy kind of coming in, maybe the question is like, why aren't you illuminating the whole top part of the sphere? Anybody? How about a back row? Anybody in the back row? So I guess, so here's a picture. I mean, it's a simple picture, but does it kind of, make sense? I've got a transmitter. So I've got some time varying magnetic fields. Yeah, I'm getting some currents, and the currents are kind of on the outside. I mean, is that what we expect, or yes or no? Or...
That should be the interface between the different conductivities.
I'm sorry?
That should be the interface between the different conductivities, and that's where the charge on the interface.
Yes, actually, in this case, however, there's no charges that are involved. So what we're seeing here is currents. So there's no current. See, there's no current that's flowing into that sphere. This is a really interesting thing, right? So when we did the DC resistivity, we actually had a current that's flowing in. This is very different. The outside of that sphere is completely resistive. So there's no currents. So all the currents are in the sphere. So there's nothing flowing through, so there's no charges that are built up. So it's an entirely different phenomenon. Anybody? Somebody has started to answer. Seem reasonable? Not? Yes? No? Why? Why are there currents in here?
Attenuation.
Exactly. Remember we talked about diffusion? Why did we do that? We talked about diffusion distance, right? At a particular time and dependent upon the conductivity. So if I've got something that's really conductive, even though I'm putting on a great big time varying flux onto it, at a particular time after I turn that off, that thing has only had a chance to penetrate a certain distance. Okay? So the higher the conductivity, the shorter that diffusion distance is. So now I come back here, and I'm like, okay, this whole thing is a big conductor, and at 10 to the minus 5 seconds, at 10 to the minus 5 seconds in that conductor, I could only have propagated in, this distance. And therefore, it actually is quite reasonable that I'm only going to see kind of the skin of what my sphere is. A little bit later, if I looked at larger times, this would have been able to diffuse in more, and we'll see that in some examples later on. Okay, so that's the first thing. You got a picture, does it make sense? Okay, kind of, okay, maybe. So now let's change the background. I made the background now 10 to the minus 2 Siemens per meter. And yeah, you can see that maybe it changed a little bit, not much. So the fact that I've got this conductive background, 10 to minus 2, hasn't really changed things very much. But what happens if I make it even more? Now you see a big difference, right? Now we start to see currents that are in here. Actually, the currents are going in a circular fashion like this. They're going into and out of the board. And I've got a lot of currents up here, and I've got reduced currents down there. And if I make this 1 Siemens per meter, I don't see my sphere. So in that case, the background has completely wiped out my ability to see the sphere. So all the currents are kind of sort of just, they're just involved with being caught up in the background. Okay, so that's well, I think I've got it summary. So that's kind of an important thing here. We've got an object in a background. If the background is resistive, it doesn't bother us very much. But as the background goes, it starts to absorb the energy, and at some point, it's going to blind me from seeing my object that way. So that's the background resistivity. Let's look to see what happens in frequency domain. So remember, frequency, no big difference. Now what I'm going to do is to look at frequencies of 10 to the 4th hertz. Here's it really resistive, and here's my current density that I see on the sphere. 10 minus 2, I see something like that. If I increase it to 0.1 siemens per meter, I get this. And if I increase it more, I get that. So exactly the same kind of phenomena that we saw in the time band. So the pictures look almost identical. So at an early time or at a high frequency, you basically see the same thing. Okay, so what have we learned? Well, we've got basics of the EM responses, talked about mutual coupling, we've got data for the frequency or time. Got a circuit model. That's a good proxy. Need to account for energy losses in the background. So let's look at a couple of field examples. So the case history that we'll try to get through today, and there might be a few hanging over to tomorrow. There's a frequency domain case history for Bupranoff. That's your Australian desalination problem for the Murray River. Kasted in Denmark for the groundwater hydrologist trying to find what the upper regions that might contain aquifer material would be, so the near surface. Helisam for anybody here works with gap geophysics. We did a mineral deposit using titanium for a deeply buried conductor. There's a really interesting case history that involves a whole host of problems and really well-defined geophysics at Magdalena. It's a minerals deposit. Also unexploded ordnance, we might not do that, but we have it. For larger scale tectonic structure, there's the Deccan traps in India where that was a grounded time domain experiment. Methane hydrate, anybody here interested in methane hydrates? Is that, so we have a case history on that. One for geothermal energy, GBR, cover case history, and come back to Mount Isa for the IP results. And also, IP is really actually surprisingly diagnostic for landfills. So that is also a problem. And certainly some places it was, and we've been to, yeah, that would be interesting. So those are the case histories. I think yeah, I think what I'm going to do is start with those are case histories we'll look at, but before we do that, we need to do something with inductive sources so that you actually see what the transmitters and receivers are like. So let's give a shot at that and see how far we can get. Huh. We have a technological problem here. Oh, yeah, sure. What? Oh, there you go. My computer can't decide why everything is upside down in the southern hemisphere here. Actually, we were doing okay till yesterday, and then I don't know, we came outside at like 6 o'clock. It was dark, right? It was like, what's going on here? Because it's summertime, of course, in the northern hemisphere. So this is time like, okay, the days are long, and it's really nice evenings. Yeah, it just caused us to do a complete jolt here.
So where were you yesterday?
Here, but day before we were in Vancouver.
Oh, awesome.
Yeah, so at some point, if I sound even more spacey than I ordinarily do, it's because like it's 3 o'clock in the morning or something, whatever. But I'm impressed with the rains you had yesterday. We went out for coffee, and it was actually quite nice. And they were sitting at coffee. It was just like this blanket of water that was coming down. Yeah. And then an hour and a half later, the sun's out, and another blanket of water.
So you're on the PDF.
What happened?
You're on the PDF right now. That'll be okay.
That's bizarre. Okay. Okay, it's all mystery. There we go. So what's our motivation here? Basically, some of the things that we'd already discussed: large areas, a whole bunch of issues with respect to groundwater. Higher resolution in the near surface. This was actually an example for petroleum engineering. Shielding problems, rugged terrain. All we want to do is we want to do something different so that we can overcome these. So we're going to just look briefly at some basic experiments, transmitters, receivers, and then we're going to look at time domain, and I'll do a groundwater problem that would do frequency domain. So here's some important questions. So now you decided, okay, you're not going to do DC resistivity, you're going to do EM. So you now have to ask these questions. And the first is always, okay, what's the target? And where is it? Is that the surface, at depth, 1D, 2D, 3D? What am I going to use for a transmitter? It's going to be the air, on the surface, waveform, frequency, or time. What's the size? What's the orientation of my transmitter? Transmitters could be big or small. Exciting the target, always have to worry about that. And geometry, coupling. So from the point of view of the receiver and the data, again, which fields to measure. Remember, now we're talking three-dimensional electric field. So we got an E field that's got 3 components, or an H field that's got 3 components. So lots of options. And then which instrument? B, DBDT, coils. So where to collect data, how many, how accurate, what's the depth of investigation, what's the footprint of the transmitter? All of these questions, and clearly there's no unique answer, but they're all kind of fall into that concept of survey design. So let's see how much headway we can make. So we got our basic experiments. We're going to have time-varying magnetic field, excite currents, measure them with the receiver. So let's first of all look at the transmitters. So if we've got large areas or rugged terrain, then we probably want to use an airborne transmitter. So there's a frequency domain system, it's called Resolve. There's time domain systems, there's a ton of them out there. One of them is called SkyTem. So in this frequency domain system, the transmitter is sitting up in here, and in the time domain system, the transmitter is just this big loop. If it's big targets, then you actually need to have a bigger transmitter. And sometimes there's ground loops that are a couple of kilometers on the side. And yeah, you're trying to find something that's really deep. This is actually the geometry of a Helisam project that we were involved with. So our transmitter, some of the key things that are involved here is like the strength of the transmitter. Remember I said that the dipole moment was equal to the current times the area. It's also multiplied by the number of turns. So if you have multiple turns, then that increases the dipole moment. The magnetic field of a dipole has this expression. So it basically falls off as 1 upon r cubed. So those are two things to remember. The moment depends on that product of current and area, and the rate that the fields fall off is 1 over r cubed. So the other thing, and because of that, we want to be as close as possible to the target. So that means that ground-based systems are the best, helicopters next, and fixed-wing aircraft are the third. And we always want to be concerned about coupling. Data and receivers could be B, could be DBDT, your choice. And in the time domain data, the primary field has got an off time, so there's a current on, shut off, and then you measure response that goes like this. Remember, this exponential decay. Here's an example for a SkyTem. So the transmitter is up here, and the receiver is actually mounted back here. See that? So the receiver is mounted over there, and then this whole thing is flown. If you're going to do it on the ground, put up this loop and then some kind of time domain current that's in there. In the frequency domain, the primary difference is that the primary field is always on. Always got the primary field going. And you need to contend with that. You either need to kind of compute what that is and subtract it out, or you need some kind of mechanical way of, often they have a bucking coil that provides a flux that's equal or opposite to the primary field from here. So that basically you measure the secondary field. And the main component here is you need to know what the positions of your transmitters and receivers. Often you just keep them in one unit. So here's that EM31 I was talking about, transmitter receiver. In the resolve system, they have a number of horizontal, like coplanar coil systems. So this coil and that coil operates at a particular frequency. The greens operate at a particular frequency. So those are coplanar coils, and you could also have coaxial coils that are kind of perpendicular. So each of these, would of course excite the Earth differently and measure different things. So where to collect data, how many, how accurate, depth of investigation. Again, these are all, as they say, part of survey design. So let's look at time domain systems. If we've got a current that is on like this and then shut off, the receiver, then the magnetic field is just going to decay. If we have measuring dBdt, then we've got kind of a spike and a subsequent decay. So we could measure, and people do. So let's talk a bit about footprint, because that's something that we got a little bit of a handle on. Is where's the currents? So we're going to use the currents as our kind of diagnostic for footprint. And those currents are going to depend upon the waveform or the frequency, as well as the background conductivity. And it's convenient. Let's just use a simple loop structure. So we've got a transmitter that's just a loop. And then we're going to look to see what the currents look like inside here. So we've got a geometry like this. So here's the Earth. We're, first of all, just going to make it a half space. At 20 meters above there, we're going to have a transmitter. And then we're going to measure a receiver on that same plane. We're going to refer to this as VMD, so vertical magnetic dipole. So a current loop, we said, looked like a magnetic dipole, and it's going to be pointing vertically, so VMD. So what we really want to know is, what do the currents look like, and how strong are the magnetic fields, because we're going to measure them up here. So the app allows you to generate this. We're going to kind of step through. We'll start off with this being 100 ohm meters, and as I said, 20 meters above for these systems. So we've got this time domain system. It's got a current. I'm going to turn it off, and then we're going to look to see what happens at a time later. So this is 0.01 milliseconds, so 10 to the minus 5 seconds. And the currents that are going to be induced in the Earth are going to have the same geometry as the currents in the loop. So they're going to be circular and centered right underneath the transmitter. And those currents are circulating like this, so they're coming out of the board here and going into the board there. They're sort of going, yeah. So I turn the transmitter off, and the currents sort of follow the same loop as the currents in the transmitter, but they're going to be now transmitted to the ground. The magnetic flux, well, we've got an idea of what that should happen, right? So you imagine a circular current that's going into another board like this, and then the right-hand rule kind of tells you what the flux looks like. So this is going to be the strength of the magnetic field, and those fields are going to go like this. So actually, the strongest location for the magnetic field is way down inside here. If you happen to be up here, that's okay. You still measure that. So what's of interest is, okay, what happens as a function of time? Okay, so I'm going to turn my transmitter off at a very early time, so 2 microseconds. Look at the currents, and they're going to be like this. So again, they're in the board, out of the board, and the strength is kind of maximum sort of up in that region in there. A little while later, 0.01 milliseconds. The currents are down here. I forgot to mention at this time here, so the diffusion distance is given by that formula that we had here, so 1260 rho. So at a particular time, at a particular rho, the diffusion distance is 18 meters. So that's kind of indicative of what we're, this is 50, so yeah, 18 meters. Another decade later, diffusion distance is 38 meters. You can see where the currents are. This one's a bit easier. And later, it's like that. Later, it's like that. So you can see what happens in the currents. So I current examples on. Start to sort of diffuse. So this was actually captured kind of theoretically many years ago. We sat in the video wrote a wonderful paper, classic, 1979, that kind of described how these currents went through. You call them smoke rings as they go down. And they go down, that's what this red line is, they sort of propagate downwards and upward. So some important points. The currents flow in the same plane as the transmitter. Currents diffuse downwards and outwards. Each transmitter's got a footprint. The maximum time, or the maximum resolution is, well, So we're going to be talking about resolution and time. What's the relationship between time and resolution and depth of penetration? So your maximum resolution is likely to occur during an experiment at the earliest time, right? Because you've got the shortest diffusion distance, so that means you've got the shortest time scales. So the maximum resolution will be at the earliest time. And then the other thing that's of interest is the depth of investigation. So that would be controlled by the latest time. So that's, yeah, it's got the time to diffuse in. So here's the earliest time. So that's your maximum resolution. The latest time, yeah, stuff is like that. So it's you know, the curves are really just kind of blurred out. So those are kind of two things that are important. Earliest time, latest time. So now let's make things just a bit more complicated and make a layered Earth. So we're going to take exactly that same phenomena, have 4 layers. So there's everything that's here is 100 ohm meters, except we're going to have an intermediate layer of different resistivities. Could be really resistive compared to this, or the same, or conductive. So we're going to make it at either 1,000, 10, or 1, and we're going to look at the currents. So here's the currents in the space where we basically got, it's basically uniform. It's 100 ohm meters. Looks like this. Okay, so now I'm going to put in a resistive layer. So I'm going to take the resistive layer in right in here. Now the question is, what do you think is going to happen? How is that going to get started? Remember, we did DC resistivity and things got really screwed up. Right? A very resistive layer.
There won't be much change in the slightly faster in that part. The diffusion was slightly faster.
That's right. So the diffusion will go more quickly through there, and importantly there's no attenuation. So let's see if that's true. The answer is right. Right. So up here, right, looks pretty much about the same as here. And then there's this kind of blank spot. There's no current. There's still electric fields. Haven't changed that. The electric fields are there. But the currents are sigma times E. So the currents are small. And then we kind of pick them up back up here. Okay, so that's what happens when I put in a resistor. And that's an important, this is like a really important aspect, because it means that if I've got an inductive system, it's not sensitive to a resistor. So I can have a big resistor there, but I don't even see it. Very different than the galvanic system. If it's a conductive layer, how is that going to change things? Okay, if you're on a roll.
You won't see, well, it'll go much slower, so you probably won't see through. It will attenuate, essentially. Diffusion.
Okay. So it's going to attenuate, but at the first crack through things here, the currents are actually concentrated in here. This is where you get your largest current. So you compare this with that, you can see that the currents minimal compared to this. They're almost all in the conductor. which is actually good. That's why, you know, EM systems are really good for finding conductors. And if we go to your next one, this is really kind of carries in spades what you were saying. I mean, not only do we get the currents in here, but they're actually attenuated. We can't get through there. So this is where the time domain, I think, is really intuitive in all of this. So we get a sense about how the currents are actually forming inside here. They don't form in resistors, and if we have a big conductor, it's just going to attenuate everything else. So that's going to be the effect of a variable. And if we look at the magnetic fields from each of these, they become complicated, but you still see something, you know, up and down. What's most informative are something called a sounding curve. So that means at a particular location, turn the transmitter off and then measure what either B is or dB/dt in a particular component. If we look at the usual one, which would be a receiver that's a coil measuring dB/dt as that component. Meters, here's the sounding. If we take that Earth with a layer of 1,000 ohms, right, you don't see anything. There's really very, very, very small changes there, very subtle. If you make a 10 ohms thick layer, then you see that the layered Earth response in the dotted line is actually quite a bit different than the background. And if you make it a 1 ohms, it's just gigantically away. So a sounding curve is really diagnostic from the point of view of trying to find a conductive layer. So if we look over a sphere, for instance, so here's our sphere, we do a time domain experiment over here. What we're looking at is a set of sounding locations at each of the dots. And there's going to be a cross section in here at which we'll have recorded the data at different time channels. So right now, at this earliest time channel, 0.025 milliseconds, as we go across here, the values are all 10 to the minus 5. And we're really not seeing this sphere here because we're, the penetration depth at that point is still just up above the sphere. And if you look at the area in plan map, it's all the same. So it basically is like 100 ohms background. If I look a little later in time, 5 milliseconds. Now if I look in plan view, it looks like that. So you can start to see, okay, there's something coming up here. And if you do a cross section through there, you see a little bit of a bump. Here's the sweet spot at about 0.3 milliseconds. So this is really nicely defined. It looks like that. So that's a really nice bump. And then now it starts to decay again. And as we go later in time, it looks like that. Okay, so what do we? So everybody's with me. So we've got a sphere. We do a whole bunch of soundings. At each sounding, we can plot what the value is at that particular time. Very early times, we just see the near surface. Mid times, we see the sphere. And at late times, everything has dissipated. We're back to nothing. Time channels would look like this. So first of all, that's sort of the basic, the takeaway thing we have to do with the fact that you're, with an inductive system, you're just really sensitive to conductors. You're not as sensitive to resistors, not completely different than than galvanic systems. So a couple of the time domain systems that are out there, there's the SkyTem system. So it's got a large loop like that and a receiver here. It has a different waveform. So the waveform, it actually has two waveforms. One is they've got a high moment system and a low moment system. So remember, low moment was the product of the current times the area. So this high moment system, as a waveform, it looks like that, has a shutoff, and then they measure time channels in this range. And the low moment, the benefits of low moment is that it cuts off a little bit early. You can decrease the ramp more quickly, and therefore you can look earlier times and get nearer surface information. So that was really the main thing there. The VTEP system has got a different kind of waveform structure. It kind of goes up and has a longer time of ramp, and then you measure it here. Let's see, do you know, are we supposed to quit at a particular time for lunch? Or?
We can talk. If you're still going, we can wait a few minutes.
Yeah, how about if let me just do one case history, so it'll be about 8 minutes, something like that. That works. Okay, good. So I do one, this will be of interest especially to people who are involved in yeah.
Just while you're on the topic, so what kind of, if any, signal processing is done on station or on the fly? In other words, you stack these on-off pulses are a certain period of time apart when the helicopter is flying along. But do you ever do any stacking of signals just to reduce noise or anything like that?
The signals are stacked. That's all done by contractors generally before we ever get them. Whether they're actually doing them on the fly in the helicopter or doing them on the ground later, actually, I'm not really sure. I think a lot of the systems just, are preset to, as they're collecting data, to just continuously stack. And you have reduced. I didn't talk about that, but you have changing polarities. Working with two polarities, so that you got currents going in one way and then switching that polarity, then you can use that to stack and get rid of like sequential noise and correlated noise that's in there. But yeah, exactly when they do, I think a lot of the receivers tend to do a lot of stacks while they're collecting the data, but not 100% sure. In ground experiments, there's more and more efforts into just simply collecting full waveform data, keeping track of everything, bringing it all back in-house, and then doing it. So this is a case history. It's casted. It's in Denmark. The kind of goal here was two things. One is to understand where the groundwater might be contained, and more importantly, they were interested in. I've got a region in here that's got a whole bunch of connections with the aquifers. If I pump out someplace, where's the water coming from? How is it going to affect a region that's nearby? So the idea is that we've got a region in Denmark, and here is a subset of that. So these lines all indicate where the SkyTep system, where that was flowing. The dotted lines are of boreholes. The sort of simplified geology looks like this. So we've got this background here that we've got are basically clays and sands and stuff like this, or basic clays. And you've got tills and And a number of different units that are coming down. So the goal is to try to distinguish where the sands and gravels are compared to the underlying clays. And then the bigger long-term goal is that, okay, if I'm sitting up here someplace and I've got a well and I'm pumping water out, where's that water coming from? And if I've got two wells here, are these guys actually going to be connecting together or not? So what I really like about this case history is that I think it takes things that extra step further with respect to the geophysics. So the geophysics is not only just to get the electrical conductivity, but actually to kind of interact with geologists and the groundwater hydrologists and to carry it forth to do a pumping test and kind of understand a little bit more how the aquifer responds. So what do we got for properties? Basically, we've got a lot of buried valleys here with clays underneath. These guys are all infilled with coarse sands and gravels. The clays underneath here are anywhere from 1 to 40 ohm meters, and anything that's up here is fairly resistive. Certainly resistivity is greater than 40 ohm meters. Ticket here, we're trying to find the top of a clay unit, conductive clay, amongst a number of resistors. So it's kind of an ideal problem, and it's really well suited from the point of view of trying to find, carrying out an airborne EM survey. So what I'm going to use here is a SkyTem system. It's got low moment, high moment. Talked a little bit about that. Here's the loop, 314 square meters, and 2 receivers, horizontal and vertical. So the data are flowing along these lines. There was, 300 line kilometers of data, 100 meter spacings, a lot of cultural noise. So before they were actually able to do anything, they did some processing on the data, removed the data that weren't particularly clean, but they still ended up with a significant number of soundings. So now what they're going to do is they're going to take each sounding and invert it. There's options here for inversion. You could do full 3D, or you could do kind of like a sequential 1D. Their processing was to use the Arhus software, and it's basically 1D inversion, but kind of laterally constrained so that the sounding here is not so different from the sounding there, and to put in geologic smoothness. So there were just under 10,000 soundings, and they were using 25 layers. So they inverted that. Now effectively we've got a 3D volume, and you can kind of slice that up and plot it in various ways. So here's a depth slice at 5 meters above sea level, and there are certain regions in here like the red. Those are all quite resistive. Remember that, and that's kind of what you were looking for, because the resistors indicated where you got the sands, gravels, that the blues are very conductive, so those are the clays. So you can see that starting to outline things. You can also look at where the high conductivity starts, really low resistivity, and plot how deep they are. And so this is a map of like the depth to the top of the clay. And you can see it's really elevation's about 40 meters here, but down in here, so these incised valleys here are actually like minus 140 meters. So these are really quite deep in here. So you got these deep incised valleys, and resistant material through them. So what they're from there, so that was sort of like the geophysical aspect that was done. So now we've got electrical conductivity, got some information, and now they can use that to effectively delineate, 18 valleys in through here. and then use that to eventually construct a hydrogeologic model. So you've got now a map, you can kind of see where things are connected. And they're going to take the resultant geophysical data that they got, and they also have some boreholes. So they're starting to be able to make a connection between like where we are, here's the borehole, here's the geophysical inversion, and now assign some not only geologic units, but also hydrogeologic properties to it. So it's a continual step, but at the end of the day, you're now able to get a three-dimensional hydrogeologic model. So you've got hydraulic permeability for a 3D model. Okay. Now once you got that, then you can connect that with a simulator, let's say mud flow, and then you can decide, okay, I'm going to pull water out of here or push water into here. And this is what they did. They took two wells. They took one here and one here, and they pulled water out of both of them. And they could see where these wells are drawing their water from. And you can see that they're almost kind of touching there, but it gives you an idea of, if I'm pumping water out, is it coming from over here, or is it down in this valley here? And that I think is, that's kind of like a really nice inroads to, it's like an end problem. That's what people are really interested in. But geophysics, electromagnetics in particular, has played a really important role in actually getting there. Yeah, so that's it. I think we should break for lunch.